Los Angeles's biggest megaprojects are reshaping the city on a staggering scale. Massive transit expansions and skyline-defining towers are converging to transform how millions move and experience LA's urban core. Today, we explore the engineering forces driving these builds, uncover the vision behind LA's multi-billion-dollar overhaul. The Metro Regional Connector is just 1.9 miles long, but its impact ripples across the entire Los Angeles basin. Beneath the chaotic sprawl of downtown, this subterranean link has silently transformed the backbone of the city's transit network. Not with flashy architecture or sweeping overpasses, but with precision tunneling and deep engineering ambition. It's a megaproject built not to be seen, but to be felt, every time a train glides through the city uninterrupted. Before this connector existed, Los Angeles had a problem. Its growing light rail system, the A, E, and L lines, stopped short of being truly regional. Trains terminated downtown, forcing commuters to transfer between lines, often in disconnected stations, wasting time and discouraging use. The system worked technically, but it didn't flow. It didn't breathe. The regional connector changed that. By boring two parallel tunnels through the dense urban core and tying together these once isolated lines, it created the first true one-seat ride across the county. Now a passenger can board in Azusa and ride directly to Long Beach. East Los Angeles to Santa Monica, no transfers, no transfer platforms, just a straight shot through the city's heart. It's a small piece of track, but a massive leap in connectivity. But connecting three major lines under a century-old city is anything but simple. Downtown LA is layered in complexity, filled with pre-existing tunnels, water mains, sewers, building foundations, earthquake faults, and a living, breathing population above. To carve a clean path through all of it, engineers had to think in three dimensions, navigating not just forward, but over, under, and around everything in their way. The answer came in the form of two tunnel-boring machines, Angeli and Elsie. Each one was a 1,000-ton beast, stretching over 400 feet long, with rotating cutter heads capable of grinding through soil, rock, and buried urban history. But the real trick wasn't speed, it was control. Tunneling through this part of LA meant passing just feet beneath sensitive structures like the historic Broadway corridor and active subway lines, where even the slightest misalignment could cause cracks or settlement. So crews worked slowly, methodically. Pressurized faces on the TBMs stabilized the ground ahead. Real-time monitoring systems tracked every vibration and movement, sending feedback to operators above. In some segments, the margin for error was less than an inch. It was engineering done with surgical precision, buried beneath a city that never stopped moving. At the surface, the work was just as intense. 3 brand new underground stations were constructed: Little Tokyo Arts District, Historic Broadway, and Grand Avenue Arts, Bunker Hill. Each of them had to be excavated in tight quarters, often amid live traffic, aging buildings, and pedestrian zones. The Little Tokyo station posed one of the greatest challenges. Crews had to demolish the existing above-ground station, reroute the tracks underground, and do it all while preserving the cultural heart of a vibrant neighborhood. Where the Port of Los Angeles meets the open Pacific, a vast transformation is underway. Once a place defined by rusted cranes and abandoned warehouses, San Pedro's historic waterfront is being reimagined as a massive public destination. This is West Harbor, a $500 million redevelopment project that's reshaping 42 acres of prime harborfront land into one of the largest and most ambitious waterfront revitalizations in California history. For decades, the San Pedro waterfront was a place of industry. Cargo ships, rail lines, and container yards dominated the landscape, cutting the community off from its own shoreline. The ocean was always there, visible but unreachable. The idea behind West Harbor was radical in its simplicity. Take land that had long been the realm of cranes and commerce and return it to the people. Replace the shipping yards with open promenades. Tear down the fences, open the gates. But turning a gritty, industrial port into a modern, urban waterfront park isn't just a matter of cosmetics. It's an enormous engineering challenge. Beneath the surface, the ground itself needed rebuilding. Years of marine traffic, heavy equipment, and salt exposure had weakened bulkheads and corroded old pilings. Before a single restaurant could open, crews had to stabilize the soil, drive hundreds of deep foundation supports, and upgrade the harbor's edge to withstand both tidal surges and seismic shocks. At the heart of the project is a massive promenade that wraps along the water, designed not just for pedestrians, but for resilience. The concrete pathways are elevated to anticipate sea level rise, with drainage systems engineered to handle storm surges from both land and ocean. New docks are being constructed to support visiting ships and harbor cruises, each one designed with floating gangways that rise and fall with the tides, maintaining access even in extreme conditions. West Harbor isn't just infrastructure, it's experience. The development includes over 150,000 square feet of space for retail, dining, and entertainment, with anchor tenants ranging from artisan markets to major restaurants. A 6,200-seat outdoor amphitheater is being built directly on the waterfront, engineered to deliver concert-quality acoustics in a coastal environment, where sound bounces unpredictably off water and wind. Engineers had to design the stage foundation to accommodate both musical events and the occasional pounding from Pacific storms, using vibration damping, materials, and reinforced steel substructures. All of this, performance spaces, restaurants, shops, sits on land reclaimed from decades of industrial use. That meant a full environmental remediation process, involving soil testing, removal of contaminated fill, and installation of modern stormwater systems to prevent runoff from polluting the bay. A particularly complex element was integrating the new West Harbor seamlessly with the surrounding transportation network. This meant widening roads, building new intersections, and coordinating with nearby freight operations, all while preserving the historic landmarks that give San Pedro its identity. The historic battleship Iowa, docked nearby, had to be factored into every phase of design, ensuring visitor access remained open during construction. The engineering teams also had to work in parallel with the Port of LA's ongoing operations, scheduling pile driving and crane activity to avoid disrupting maritime logistics. Even as the heavy machinery rolls and concrete is poured, the bigger vision is already taking shape. This isn't just about leisure. It's about reconnecting a city with its coastline. For generations, San Pedro's waterfront was a wall of industry. West Harbor turns it into a front porch. It's not every day that a space shuttle becomes the centerpiece of a construction site. But in Los Angeles, the Samuel Oschin Air and Space Center is being built quite literally around one. This isn't just another museum wing. It's a $400 million purpose-engineered megastructure designed to permanently house Space Shuttle Endeavour in launch position, standing vertical, with its twin solid rocket boosters and external fuel tank assembled in full. That image alone, an actual NASA shuttle poised for flight in the middle of the city, captures the scale and ambition of the project. But what's happening behind the scenes is even more dramatic. To erect a building capable of not only supporting, but displaying a 20-story tall spacecraft in full stack, required a deep rethinking of what a museum could be. The Samuel Oschin Air and Space Center isn't just a container for artifacts. It's a structural achievement in itself. Construction began with a massive excavation, clearing out enough space to lower the shuttle's components into position before any part of the building could rise around them. Because Endeavour cannot be easily moved or lifted vertically after assembly, the engineering team had to plan everything in reverse. The shuttle stack would be lowered into a custom-built foundation pit, bolted into seismic isolation systems, and only then would the rest of the building go up, literally built from the inside out. The foundation had to be a feat of precision. Los Angeles is earthquake country, and you don't suspend a 300,000-pound shuttle on top of soil without serious reinforcement. Deep piles were driven dozens of feet into the earth, and a complex base isolation system was designed to decouple the shuttle from ground motion in a major quake. Surrounding that is a structural steel frame capable of supporting massive loads at extreme heights, while also preserving the open interior space needed to give visitors a clear view from every level. But that was just the start. The center's superstructure is a blend of heavy steel trusses and composite materials, designed to handle both the visual weight of the shuttle and the real-world stress of housing dozens of other large aerospace vehicles, including jets, capsules, satellites, and even a flying laboratory. Each exhibit element needed rigging points and floor loading that far exceed standard museum specs. Some sections of the floor were designed to handle more than 250 pounds per square foot. The roof, spanning a massive clear height to allow for the shuttle's vertical profile, had to be engineered for both strength and subtlety. It uses a combination of deep-span steel girders and cross-bracing to support lighting systems, HVAC ducts, and suspended aircraft displays, all without obstructing the shuttle view. Installing that roof without damaging the delicate shuttle components below required a phased lift strategy, using temporary supports and synchronized cranes to maneuver the beams into place with just inches to spare. Tucked just south of downtown Los Angeles, Exposition Park has always been a place of ambition, home to world-class museums, the LA Memorial Coliseum, and the beating heart of the city's cultural and sporting life. But what's unfolding there now isn't just an upgrade. It's a full-scale transformation, timed to align with the arrival of the 2028 Olympic Games. This is the Exposition Park expansion, and it's one of the most concentrated, multi-layered megaprojects happening anywhere in the city. We're talking about more than 100 acres of dense, high-profile development, the kind of space where architecture, infrastructure, landscape, and engineering have to work in seamless coordination, and every inch of it is being reimagined, stitched together into a new kind of urban park, one that blends Olympic-scale sports facilities with civic space, transit access, and cultural presence. At the center of this expansion is the Lucas Museum of Narrative Art, an enormous, fluid, almost spaceship-like structure that defies traditional design logic. Spanning over 300,000 square feet, the building floats above the landscape on concrete pylons, allowing for an uninterrupted park to run beneath it. Engineering that vision into reality meant solving a long list of structural challenges. The museum's form curves and bends with few right angles, requiring a steel skeleton unlike any conventional grid. Every beam had to be custom fabricated. Load paths had to be recalculated from scratch. But that's only one piece. Adjacent to it, new Olympic training facilities are being added in and around the Coliseum, including athlete, housing, high-performance sports labs, and temporary structures built to IOC standards. These aren't off-the-shelf projects. Each facility must meet international competition criteria while being adaptable for post-games public use. That means flexible infrastructure, modular designs that can expand or collapse depending on future needs, and utility corridors capable of serving both a global broadcast event and a local youth sports league. A new mobility hub is also under construction, tightly integrated with the K Line, Crenshaw LAX Line, regional bus service, and pedestrian corridors linking USC, the Natural History Museum, and BMO Stadium. This isn't just about moving people, it's about rethinking access. Engineers are embedding smart traffic systems, ADA upgrades, secure bike lanes, and crowd flow modeling to handle Olympic-scale surges without overwhelming local streets. Then there's the landscape itself. More than 14 acres of new green space are being carved into the existing grid, with bioswales, permeable pavement, and stormwater recycling systems hidden beneath sculpted terrain. Everything is dual purpose. That shaded plaza? It's also an emergency egress route. That rolling hill. It's backfilled over a utilities corridor with seismic isolation joints. Every tree and trail was designed not just for beauty, but for function, cooling microclimates, guiding crowds, and managing runoff during rare but intense LA storms. Beneath the surface, the engineering complexity continues. Utility upgrades, electric, water, fiber, gas, are being laid out like a circulatory system for a future-proof urban core. Crews had to dig and trench with surgical accuracy, often working just inches away from existing structures that couldn't be moved or shut down. Phasing the construction without interrupting events at the Coliseum or the Museum District meant round-the-clock scheduling, heavy prefabrication, and just-in-time delivery logistics. Olympic Plus Hill isn't subtle. At 760 feet tall, it's one of the tallest residential towers ever built in Los Angeles. An enormous vertical structure that carves its presence directly into the downtown skyline. Located at the crossroads of Olympic Boulevard and Hill Street, this project is pure scale. Over 800 residential units, 60 stories, and more than 1 million square feet of combined residential, retail, and amenity space. But the story here isn't just size. It's how engineers managed to build something this massive in the seismic heart of California. The foundation work alone pushed limits. To support the weight of the tower, deep piles had to be drilled through layers of soft fill and clay until reaching bedrock, some driven more than 80 feet into the ground. The base isn't just strong, it's smart. A reinforced concrete core, wrapped in steel and designed with shear walls, creates a seismic-resistant spine capable of swaying without breaking. That's essential in a city where ground movement isn't a possibility, it's an inevitability. Once the base was in place, construction moved upward at a rapid pace. Crews used self-climbing formwork systems that latch onto the tower's core, lifting themselves with each pour of concrete. Every floor was built in a tight cycle. Pour, cure, lift, repeat, often turning around a new floor in under 5 days. Each level had to align perfectly, not just vertically, but in terms of internal systems. Plumbing, electrical, fireproofing, and post-tensioning cables all had to be laid out with centimeter-level precision. The tower's skin, a curtain wall system made of high-performance glass and aluminum, presented its own set of challenges. At 60 stories, installing massive panels of glass isn't just dangerous, it's a logistical problem. Wind conditions shift rapidly at height, and each panel had to be lifted by crane and installed within narrow time windows to avoid delays. The glass isn't just aesthetic, it's engineered for insulation, glare reduction, and earthquake flexibility, with anchor points that allow for controlled movement. Olympic Plus Hill also demanded an advanced vertical transportation system. With so many units stacked vertically, elevator wait times could have crippled usability. To solve that, engineers installed high-speed traction elevators managed by a destination dispatch system, software that assigns elevators based on passengers' final destinations rather than button presses. It reduces stops, speeds up trips, and keeps the tower moving efficiently even at peak times. Parking and access were another challenge. With limited surface area and thousands of potential residents and visitors, a multi-level underground parking structure was integrated into the base, complete with car stackers and electric vehicle charging systems. Coordinating excavation and support for that structure, while still maintaining the structural integrity of surrounding streets, required careful sequencing and real-time monitoring of ground pressure and movement. Jordan Downs wasn't built to last, but it lasted. What began in the 1940s as temporary war worker housing in the heart of Watts evolved into one of Los Angeles's most recognized public housing projects. For decades, it stood as a symbol of neglect, of disinvestment, of the city's fractured promises. Now it's at the center of one of the largest and most complex urban redevelopments ever attempted in Southern California. This is the Jordan Downs redevelopment, a multi-phase billion-dollar megaproject that's rebuilding an entire neighborhood from the ground up. We're not talking about a simple renovation. This is full-scale urban reconstruction, replacing over 700 aging public housing units with a mixed-income community of more than 1,400 new homes, complete with parks, retail corridors, a new street grid, and state-of-the-art infrastructure. And all of it is happening while people still live there. That reality, redeveloping a live-in community without displacement, is what makes this project such a massive logistical and engineering challenge. Everything had to be phased. Crews couldn't just level the site and start fresh. Instead, new housing blocks were constructed in stages on available land, allowing families to relocate within the community as old units came down. That required intense coordination, not just in construction, but in utilities, access roads, and safety systems, all while keeping the neighborhood functioning. Before any new buildings could rise, the land itself had to be re-engineered. Jordan Downs sits on a former industrial site, contaminated from decades of adjacent manufacturing. That meant full environmental remediation, soil testing, removal of hazardous material, groundwater management, and installation of protective barriers. Engineers excavated tens of thousands of cubic yards of earth, replacing contaminated soil with engineered fill, compacted and monitored for stability. Next came infrastructure. The original Jordan Downs layout was a relic of mid-century planning. Isolated blocks with limited connectivity and almost no integration into the surrounding street grid. To fix that, the project involved installing an entirely new road network, complete with sidewalks, bike lanes, storm drains, and underground utilities. A major extension of Century Boulevard now runs through the site, connecting it to the broader Watts area and giving the community a direct arterial link to the rest of the city. Structurally, the new buildings are designed for both density and resilience. Wood frame over concrete podiums dominate the design, balancing cost efficiency with seismic durability. Each structure is engineered with fire suppression systems, earthquake-resistant framing, and energy-efficient insulation to meet California's Title 24 building codes. Sustainability was also baked in. Solar panels, drought-tolerant landscaping, and stormwater capture systems are integrated across the site. And unlike the original layout, The new Jordan Downs is being built with mixed-use development at its core. A central retail village is part of the plan, complete with grocery stores, cafes, and community-serving businesses. That required additional engineering for load-bearing slabs, commercial-grade ventilation, and enhanced utility access to support food service and retail operations. The project also includes new parkland, recreational facilities, and space for schools and job training centers, all of which had to be laid out on what was once a closed, fenced-off grid. The G Line, formerly known as the Orange Line, was never designed to stay the same. From the beginning, it was a workaround, a bus rapid transit route built in place of a rail line due to funding constraints and political compromise. But over time, its ridership and strategic location forced the city to rethink what it could be. Now the G Line is undergoing a major transformation, an infrastructure upgrade project spanning the entire 18-mile corridor through the San Fernando Valley, pushing the limits of what bus transit can do in Los Angeles. The goal is simple: increase speed, capacity, and safety. But executing that goal has required deep and complex engineering interventions at nearly every point along the route. One of the most critical changes is the installation of a state-of-the-art signal priority and preemption system. Unlike traditional traffic signals that respond to fixed timers or limited sensors, this system actively clears intersections ahead of approaching buses, reducing delays and allowing for smoother flow across dozens of street crossings. Another major element is the construction of grade separations, rail-style overpasses and underpasses at the busiest and most delay-prone intersections. Key locations like Sepulveda Boulevard, Van Nuys, and others are being excavated and rebuilt with concrete bridges and undercrossings to allow buses to pass through without ever stopping for cross-traffic. These structures require complex retaining wall systems, traffic rerouting, and in some cases, full reconstruction of local street infrastructure around the new grades. To support higher frequency service, the corridor is being outfitted with new power systems, bus-only lanes resurfaced with heavy-duty concrete, capable of supporting constant vehicle weight, and upgraded station platforms. The existing asphalt guideway, originally built to mimic light rail tracks in layout, has been deteriorating under the strain of articulated buses. Rebuilding it requires full-depth removal and replacement with reinforced concrete slabs, tied into a subsurface drainage system to prevent water intrusion and pavement shifting over time. Platform upgrades go beyond aesthetics. Stations are being lengthened to accommodate longer, higher-capacity buses and future electric models. Each platform is being raised and re-leveled to allow for near-zero gap boarding, speeding up passenger flow and improving accessibility. Integrated electrical conduits and utility vaults are also being installed during construction to prepare for future overhead charging systems as the fleet transitions to full electric. A core part of the upgrade involves upgrading the actual vehicle fleet. Metro is phasing in battery electric buses with larger passenger capacities, regenerative braking systems, and onboard diagnostics. These buses weigh more than their natural gas predecessors, which has direct implications for bridge loading, braking distances, and pavement wear. Engineers had to revisit structural tolerances across the entire corridor, from culverts and embankments to turning radii and clearance zones, to ensure long-term durability under heavier rolling stock. Fiber optic lines are also being laid alongside the corridor to support real-time monitoring. Everything from vehicle location, signal interaction, passenger load, and environmental data will be fed into Metro's central control center. This data will be used not just for dispatch, but to dynamically adjust signal cycles and reroute in case of emergencies. Drainage systems along the G line were never built for current-day storms. As part of the upgrade, culverts are being expanded, bioswales are being added to medians, and runoff channels are being lined with concrete and fitted with sensors to monitor flow levels during heavy rain. All of this is necessary to prevent trackway flooding and preserve the subgrade from erosion. Brightline West isn't an idea, it's under construction. A $12 billion high-speed rail megaproject designed to link Los Angeles to Las Vegas in just over 2 hours, cutting a trip that often takes over 5 by car. With speeds reaching 200 miles per hour and over 260 miles of new rail corridor, this is one of the largest and most complex infrastructure projects ever attempted in the American Southwest. The alignment runs primarily along the I-15 corridor, chosen for its straight path, existing right-of-way, and the massive volume of traffic it sees. Over 50 million people travel between LA and Las Vegas each year, many of them stuck in stop-and-go congestion. Building next to a major interstate, however, comes with logistical and engineering demands on a different scale. Crews must work within narrow margins between freeway traffic and construction zones, requiring extensive concrete barriers, temporary detours, and phased sequencing to avoid bottlenecks. The trains will operate entirely on dedicated, grade-separated track. That means no level crossings, no signal delays, and no sharing with freight or commuter rail, making Brightline West a true high-speed rail system by global standards. To achieve this, over 300 structures are being constructed along the route, including overpasses, bridges, wildlife crossings, and viaducts. Every one of them is engineered to withstand extreme desert heat, high wind speeds, and seismic loads consistent with California building codes. One of the most technically demanding sections involves crossing the Kaijon Pass, an elevation climb of over 3,000 feet between the Inland Empire and the high desert. This stretch requires extensive cut-and-fill operations, retaining walls and reinforced embankments. Specialized track design, including banked curves and controlled gradients, ensures that trains maintain high speeds without overstressing the vehicles or the infrastructure. Trackbed construction is another layer of complexity. Unlike conventional rail, high-speed systems require exacting tolerances for smoothness and alignment. The subgrade must be compacted and stabilized to millimeter-level accuracy, followed by multiple layers of ballast, reinforced concrete slab track, and vibration-damping materials. These systems are monitored in real time through embedded sensors, allowing for predictive maintenance and immediate response to deviations. Powering the system is an electrified catenary line running the full length of the corridor. This requires constructing hundreds of miles of new transmission infrastructure, including substations, overhead gantries, and high-voltage feeds. To ensure uninterrupted service, the power supply is designed with built-in redundancy and real-time switching capabilities. Utility coordination across 2 states and multiple counties adds further layers of complexity to every mile built. The train sets themselves, based on Siemens Velaro or similar European high-speed rail platforms, will be custom-modified for American standards. Each unit will feature aerodynamic nose cones, regenerative braking systems, crash energy management structures, and lightweight aluminum bodies to reduce axle load and track wear. These aren't commuter trains. They're precision-built machines designed to run at 200 mph across open terrain, with acceleration, deceleration, and safety systems modeled after Japan's Shinkansen and Germany's ICE.
Rail of Sound Transit 3 demands a construction strategy that spans decades, integrates multiple jurisdictions, and aligns civil, systems, and structural engineering disciplines across a vast and varied geography. This voter-approved expansion of regional transit infrastructure in the Puget Sound area includes new light rail lines, commuter rail improvements, and bus rapid transit corridors, all designed to accommodate a rapidly growing metropolitan population and its shifting transportation needs. At the core of Sound Transit, 3's physical execution is the construction of hundreds of miles of new guideway, some elevated, some underground, and others at grade, depending on topographic and urban constraints. In urban centers like Seattle, tunneling is a dominant component, requiring the use of tunnel boring machines launched from deep access shafts. These shafts are constructed using secant, pile, or diaphragm wall methods, followed by excavation and concrete base slabs to support TBM assembly. As each tunnel progresses, precast segmental lining is installed immediately behind the cutter head, and grout is injected into the annular space to stabilize the ground and ensure watertightness. In suburban and exurban areas, elevated guideways are more cost-effective and less disruptive. These are constructed using precast segmental box girders, supported on piers founded on drilled shafts or driven piles. Span-by-span erection methods, including balanced cantilever or launching gantries, are used to minimize construction footprint and expedite the schedule. Each pier is precision-aligned to maintain track geometry, and expansion joints are incorporated to account for thermal movement and seismic activity, critical factors in the seismically active Pacific Northwest. At-grade sections, while more straightforward to build, require extensive utility coordination, signal integration, and roadway modifications. Track slab construction includes sub-ballast, geotextile membranes, and continuous welded rail affixed with elastomeric fasteners for noise and vibration control. Crossings at intersections include embedded track panels and are integrated with intelligent transportation systems for preemption and safety. Station construction across the Sound Transit 3 network varies by location and function. Urban stations often require deep excavation and support of excavation systems such as soldier piles and lagging or secant piles. Platform construction includes structural slabs, canopy systems, tactile guidance elements, vertical circulation components such as elevators and escalators, and integrated fare control areas. Suburban and elevated stations are typically built on structural steel or precast concrete platforms, allowing for faster modular assembly. Mechanical and electrical systems, ventilation, fire suppression, power distribution, and communications are standardized across the network but require bespoke design at each site to accommodate geography and usage. Overhead contact systems for power delivery are strung on catenary poles or integrated into tunnel soffits using rigid conductor bars. Signaling systems use automatic train control with centralized monitoring and dispatch centers, all fiber connected through continuous cabling installed alongside track or in dedicated utility conduits. The Sound Transit 3 program is being delivered in carefully sequenced phases, with each segment undergoing planning, environmental clearance, design, procurement, and construction on overlapping timelines. Coordination with local utilities, city planning departments, and environmental agencies is ongoing throughout the life cycle. Simultaneously, worksite safety, noise control, and public interface management are embedded into each contract package to minimize community disruption. Transforming set against the wide-open expanse of eastern Nevada, the Spring Valley Wind Farm was developed to capture the region's steady wind resources and convert them into utility-scale electrical power. Building such a facility began with a detailed wind resource assessment using meteorological towers to gather multi-year data on wind speed, direction, and turbulence intensity. This information guided the precise placement of each turbine to maximize efficiency while minimizing interference between units. Before installation could begin, the site underwent grading and road construction. Access roads had to be engineered for heavy transport loads, as turbine components, blades, towers, and nacelles are among the largest and heaviest pieces of equipment moved over land. The roads were designed with gentle curves and controlled gradients to accommodate the specialized trailers used for hauling blades that can span well over 100 feet in length. Foundations for each turbine required deep excavation to reach stable soil strata, followed by the placement of reinforced concrete pads. The circular foundations were heavily reinforced with steel rebar cages designed to resist overturning forces generated by wind loads on the tower. Anchor bolt assemblies were precisely positioned to match the base flange of the tower sections. After concrete placement, a curing period ensured that the foundation reached its full design strength before tower erection began. The tower installation process was conducted in segments, typically 3 to 4 cylindrical steel sections lifted into place by high-capacity crawler cranes. Precision alignment was critical, with each section bolted and tensioned to exact torque specifications. Once the tower was complete, the nacelle, housing the gearbox, generator, and control systems, was hoisted to the top. Blade installation was one of the most technically challenging steps, often requiring calm weather conditions for safety. Each blade was bolted to the hub, and the completed rotor assembly was lifted and attached to the nacelle's main shaft. Electrical cabling inside the tower connected the generator to underground power lines, which routed energy to a substation. At the substation, transformers stepped up the voltage for transmission over long distances, and control systems monitored the performance of each turbine in real time. Data from sensors on the nacelle and blades fed into a centralized control center, allowing operators to adjust blade pitch and yaw to optimize energy capture. When fully operational, the Spring Valley Wind Farm stood as a coordinated network of mechanical and electrical systems, engineered to operate reliably in the region's unique wind patterns and contribute clean, renewable power to Nevada's grid for decades to come. What set the Darlington Small Modular Reactor project apart from the beginning was its use of a fully licensed, pre-developed nuclear site, something exceedingly rare in the nuclear industry. The Darlington Nuclear Generating Station in Ontario had long maintained a site preparation license for future expansion, which streamlined early regulatory processes for the Small Modular Reactor, or SMR. This advantage allowed project teams to initiate earthworks and enabling infrastructure much earlier than would typically be possible for a new nuclear build. Initial site development began with large-scale excavation to accommodate the reactor island, turbine structures, and support facilities. Rock blasting and removal were required to reach the design depth for seismic and flood protection. The site lies near Lake Ontario, so hydrological modelling informed the grading strategy and stormwater detention systems. Extensive cut and fill balancing was undertaken to minimise material export and optimise the site's profile for future service roads and vehicle access. Subsurface characterisation was essential for the foundation design of the SMR. Geotechnical boreholes and core sampling provided detailed profiles of the limestone bedrock and glacial till overlay. Once the excavation reached bedrock, foundation work began with rock anchors, concrete mud slabs, and waterproofing layers. The nuclear island foundation required a heavily reinforced concrete mat slab designed to distribute high concentrated loads from the reactor vessel and containment structures. The SMR selected for Darlington is a pressurized water reactor with integrated steam generation and passive safety features. The reactor building is being constructed using modular components prefabricated off-site, including sections of the containment structure, equipment modules, and piping skids. These modules are shipped by rail or specialized trucks and assembled using heavy lift cranes on engineered laydown pads adjacent to the foundation. The modular approach dramatically reduces on-site labor requirements and improves quality control by shifting fabrication into controlled environments. Containment and auxiliary buildings use thick reinforced concrete walls with embedded steel liners and seismic isolation joints. Key safety systems, such as the passive heat removal system, emergency core cooling, and spent fuel cooling are embedded in compact configurations to allow for the SMR's reduced footprint. Embedded conduits, grounding grids, and shielded penetration sleeves are installed in formwork before concrete is poured, ensuring precise alignment and shielding performance once complete. The turbine island, located adjacent to the reactor building, is built on deep foundations and houses the generator, condenser, feed water heaters, and auxiliary equipment. Although the power output of an SMR is smaller than traditional nuclear units, the turbine equipment must still meet exacting standards for steam quality, thermal cycle efficiency, and vibration performance. Heat rejection is handled through mechanical draft cooling towers with high-efficiency fans and drift eliminators, positioned to avoid fogging and icing in prevailing wind conditions. Grid connection infrastructure includes switchyards, step-up transformers, and control systems, all housed in electromagnetically shielded buildings. A centralized control facility oversees both reactor and balance of plant systems, using digital instrumentation and control platforms with redundant safety class architectures. A few engineering feats that match the complexity and precision required to lift a functioning roadway within an existing bridge arch, all while keeping maritime and vehicular traffic moving. The Bayonne Bridge, Raise the Roadway project was exactly that kind of endeavour, a surgical transformation of a legacy structure to meet the demands of modern commerce. Originally opened in 1931, the Steel Arch Bridge connecting Bayonne, New Jersey to Staten Island, New York had a vertical clearance insufficient for newer Panamax and post-Panamax container ships to pass beneath. Rather than demolish and rebuild, the project team pursued an extraordinary solution. Raise the roadway from its original elevation to a new, higher level, without altering the historic arch. The operation began with extensive structural assessments of the existing steel arch, whose riveted trusses were still in remarkably good condition. The original roadway deck hung from vertical suspender cables connected to the arch's underside. These suspender cables were gradually unloaded as crews prepared for the insertion of an entirely new deck system, this time supported above the old roadway and suspended higher within the arch span. Construction began with the fabrication of steel support columns and crossbeams anchored to the existing arch ribs. These temporary and permanent steel components were staged off-site and moved into place with extreme logistical care, as space was limited and much of the work had to be performed from barges or scaffolding. A critical step involved the staged demolition of sections of the original roadway, which were removed incrementally while traffic continued on other lanes. The demolition had to avoid disturbing the live structural behavior of the arch, meaning that counterweights, temporary supports, and load redistribution were all carefully engineered for each phase. After the initial segments were cleared, the new roadway deck segments were installed section by section, elevated well above the original deck level. These new segments utilized orthotropic steel panels with welded ribs to minimize weight while maximizing stiffness, allowing for long spans between vertical supports. To complete the transition, the team had to construct new approach ramps on both sides of the river that gradually transitioned from the existing ground level to the newly elevated bridge deck. These approaches were supported by drilled shaft foundations and used cast-in-place concrete piers and precast girders. Each piece had to align precisely with the central span deck geometry to maintain smooth grade transitions and proper drainage slopes. One of the most impressive features of this project was the uninterrupted use of the bridge throughout much of the work. A movable, temporary trestle system allowed traffic to continue using the bridge, even as sections of the original deck were removed and replaced. This required careful scheduling, custom staging platforms, and constant monitoring of structural loads to avoid overstressing any part of the arch. Instead of dismantling an aging bridge and replacing it with a new one, engineers tasked with the Bayonne Bridge, Raise the Roadway project, chose an unprecedented path, building a higher roadway within the existing arch structure, all while keeping traffic flowing and preserving the historic character of the original span. This decision was driven largely by the need to accommodate the larger container ships enabled by the expansion of the Panama Canal. The original vertical clearance of the Bayonne Bridge, which stood at approximately 151 feet above mean high water, was no longer sufficient to support this new class of vessels accessing the Port of Newark and Port Elizabeth. Raising the clearance to nearly 215 feet became a logistical imperative. The existing bridge's steel arch, a landmark engineering structure from the early 20th century, presented both opportunities and limitations. Its structural integrity remained excellent, allowing it to be repurposed to support a new, elevated roadway. The challenge was that the original deck hung from vertical suspenders below the arch's apex. To raise the roadway, engineers devised a complex method of constructing a new deck above the original without disrupting either maritime activity below or vehicular activity above more than absolutely necessary. The process began with the construction of a series of temporary support structures within the arch, allowing workers to access both the existing deck and the new construction zone above it. New piers and approach structures were simultaneously being constructed at both ends of the bridge using reinforced concrete columns supported on deep foundations, often drilled shafts socketed into bedrock. These approaches would eventually tie into the new elevated roadway. Once temporary supports were in place, workers began erecting steel framing for the new upper roadway within the arch span. This framing consisted of longitudinal girders and crossbeams bolted and welded into position, followed by installation of orthotropic deck panels. These panels were fabricated off-site and trucked in for precise placement, reducing on-site assembly time and improving quality control. The steel deck design provided a lightweight yet structurally robust solution that minimized additional loading on the arch. Throughout this process, extensive structural analysis was continuously performed to ensure that loads were properly transferred through the original arch structure. Sequencing was essential. As the new deck was installed section by section, old portions of the original deck were removed underneath in a carefully planned reverse progression. Traffic was maintained through the use of temporary roadways and weekend closures scheduled around critical lift and removal operations. Seismic upgrades, drainage improvements, lighting systems, and safety features were all integrated into the new deck, bringing the structure up to modern standards without compromising the visual profile of the historic arch. Once the elevated roadway was fully connected to the new approaches, the bridge could serve modern truck traffic and massive container ships alike, without ever having lost its central role in the region's infrastructure. Towering over the Atlantic Ocean, approximately 27 miles off the coast of Virginia Beach, the Coastal Virginia Offshore Wind Project is making history in 2025 as the largest offshore wind farm currently under construction in the United States. With a planned capacity of 2,600 megawatts, it is scheduled for full commissioning by the end of this year, marking a significant leap forward in large-scale renewable energy deployment along the eastern seaboard. The project encompasses 176 wind turbines spread across a lease area of over 112,000 acres of federal waters. Each turbine is mounted on a monopile foundation driven deep into the seabed using heavy-lift jack-up vessels, equipped with pile-driving hammers rated for deep-water installation. These steel monopiles are engineered to resist harsh marine loads, including hurricane-force winds and powerful Atlantic swells. The turbines themselves rise over 800 feet from the sea surface to blade tip, and each rotor spans more than 700 feet in diameter, capturing enormous volumes of kinetic energy. Construction progresses in coordinated marine campaigns, with foundation installation occurring first, followed by tower sections, nacelle placement, and finally blade assembly. Specialized feeder barges transport pre-assembled components from staging ports along the Virginia coast to the offshore site. Timing these operations requires minute-by-minute weather window forecasting, as high sea states or wind speeds can delay crane operations for days. Marine logistics command centers monitor vessel movements and schedule activities in tight sequences to maximize efficiency during fair weather periods. Subsea electrical infrastructure is another critical component under construction in 2025. High voltage export cables are laid along the ocean floor using plow and trenching systems, buried beneath the seabed for protection against anchor drag and trawling gear. These cables extend from offshore substations back to the shore landing point at Camp Pendleton in Virginia Beach. From there, the power is transmitted to a new onshore switching station and into the regional grid operated by PJM Interconnection. Each offshore substation is a multi-story platform mounted on its own jacket foundation. These substations collect medium voltage power from groups of turbines, transform it to high voltage, and transmit it inland. Engineering these structures requires close attention to structural stability, corrosion resistance, and remote operability in extreme conditions, with all systems accessible for maintenance by crew transfer vessels and helicopters. Final commissioning work in 2025 includes electrical energization of circuits, system synchronization, performance testing, and integration with grid management systems. Marine wildlife monitoring and mitigation measures continue in parallel, ensuring compliance with environmental regulations during the final phases of construction.
On the eastern edge of San Francisco, where rusted cranes once loomed over a forgotten stretch of Shipyard, the Pier 70 redevelopment is one of the city's most ambitious megaprojects currently under construction in 2026. This historic industrial zone, nestled between the Dogpatch neighborhood and the bay, is being transformed into a vibrant waterfront community, one that blends housing, jobs, public parks, and restored heritage structures into a single cohesive district. The construction underway this year marks the most active phase of the project to date, with key milestones approaching as the site charges toward completion in the early 2030s. As of 2026, multiple parcels across Pier 70 are under simultaneous construction. Residential towers are climbing skyward, with the first phase of housing expected to be completed by 2027. These buildings will deliver nearly 1,100 homes in their initial stage, 25% of which are reserved as affordable housing. Construction crews are also working on major infrastructure upgrades across the site, including new streets, transit corridors, pedestrian paths, and shoreline protections to guard against sea level rise. The heart of the mega project is its connection to the past. Pier 70's redevelopment in 2026 doesn't erase its history, it builds on it. Several historic buildings are being restored and repurposed. These include old machine shops and steel foundries that once supported the shipbuilding industry. In 2026, many of these structures are undergoing seismic retrofitting and interior renovations to be converted into arts venues, retail hubs, and office space for design and tech firms. The goal is to preserve the gritty industrial character of the site while making it usable and vibrant for a 21st century city. Public space is a major focus of the construction effort in 2026. Over 9 acres of parks and waterfront access points are being built across the site. The highlight will be the large central green, an expansive park framed by restored industrial sheds and framed by views of the bay. As of this year, grading, drainage, and landscaping are underway, with full park openings projected for 2028. These open spaces are being built to double as climate infrastructure, designed to absorb stormwater, manage heat, and protect the site from flooding. In addition to housing and public amenities, the commercial component of Pier 70 is actively rising. Office buildings tailored to life sciences, technology, and creative industries are under construction now, with tenants expected to begin moving in by 2027-2028. These buildings are designed with flexibility in mind, featuring adaptive floor plans, outdoor terraces, and energy-efficient systems. Construction in 2026 is focused on delivering the first phase of these workspaces, helping to establish Pier 70 as an employment hub linked directly to the city's evolving economic base. The location is also a key asset. In 2026, construction crews are coordinating with transit agencies to enhance connections between Pier 70 and the rest of the city. Muni lines, bike lanes, and pedestrian links to the nearby Dogpatch neighborhood are all part of the ongoing infrastructure work. There's also future planning underway to accommodate ferry service, which would further connect the development to the regional transit network. When fully completed in the early 2030s, the Pier 70 redevelopment will deliver over 2,000 housing units, 2 million square feet of office and commercial space, 9 acres of parks, and over 300,000 square feet of retail, cultural, and community uses. But in 2026, it's the construction activity that defines the project. Foundation work, steel framing, historic preservation, and shoreline transformation all unfolding simultaneously.
Launching a new light rail system in a rapidly urbanizing environment like Austin, Texas, demands a tightly orchestrated series of construction phases, each calibrated to balance public disruption, environmental stewardship, and long-term transit capacity. Project Connect Light Rail, central to the city's broader transportation strategy, represents a blend of civil infrastructure, systems integration, and urban design. Its construction is not only about laying tracks, but also about reconfiguring the city's mobility framework from the subgrade utility level all the way up to station canopies. Initial phases of the work required a thorough utility mapping and relocation campaign, especially in downtown Austin, where decades of layered infrastructure, water mains, electric duct banks, storm drains, and fiber optic lines occupied the corridors targeted for track alignment. Crews deployed vacuum excavation techniques and ground-penetrating radar to verify as-built conditions, followed by jack and bore and open-cut trenching to shift essential services out of the right-of-way. This preliminary but crucial step enabled the mainline guideway construction to proceed without repeated conflicts or delays. As alignments were cleared, trackbed preparation commenced with excavation, soil stabilization, and sub-ballast installation. In sections where the light rail operates at grade, the track slab was constructed using reinforced concrete with embedded direct fixation fasteners, allowing for precise gauge control and long-term durability under repeated thermal and dynamic stresses. In downtown segments, where aesthetic and spatial considerations dominate, tracks were encased in special surface treatments, integral colored concrete, brick pavers, or textured asphalt, to blend seamlessly with pedestrian zones while maintaining proper clearance envelopes and safety delineations. Where the alignment transitions onto elevated guideways or bridges, segmental box girder construction was utilized. Precast segments were manufactured off-site in controlled environments, then transported to staging areas and erected using launching gantries or crawler cranes, depending on site access constraints. These structures had to be designed for both dynamic train loading and lateral wind forces, while also accommodating future utilities and maintenance walkways. Each segment connection used post-tensioning tendons and epoxy joints to ensure monolithic performance and structural integrity. Stations themselves were constructed with a modular approach, precast platforms, canopy structures, and mechanical cores delivered to site and installed with minimal wet trades. ADA compliance, passenger safety, and urban connectivity guided the architectural layout, with integrated drainage systems, tactile strips, wayfinding systems, and lighting installed as part of the core station package. At intermodal hubs, construction was further complicated by the need to synchronize with bus bays, parking structures, and bike ped infrastructure. Power and signaling installation occurred in parallel with guideway and station build-out. Overhead catenary systems were supported by steel poles anchored into micro-pile or spread footing foundations, with tensioning devices calibrated for thermal expansion ranges. Communications-based train control systems were integrated along the alignment with underground fiber routes, trackside equipment cabinets, and centralized operations centers ensuring constant feedback and real-time train location monitoring. Breaking ground on a regional freight mobility program spread across a vast expanse of desert terrain in southern Nevada. The Copper Mountain Solar Complex represents a large-scale application of photovoltaic technology built in multiple phases to steadily increase generation capacity. Each expansion began with extensive site grading, where bulldozers and graders prepared the ground to ensure uniform slopes for drainage, while preserving the structural stability needed to anchor thousands of solar panel arrays. Given the desert environment, dust suppression was a continuous concern during earthwork, requiring water trucks to regularly dampen surfaces without creating erosion. The mounting system for the panels was engineered for both durability and precision alignment. Steel support posts were driven into the compacted soil using pile-driving rigs equipped with laser-guided systems to ensure exact placement. The arrays were organized in long, continuous rows to maximize exposure to the sun's path, with spacing calculated to prevent self-shading at low solar angles in winter months. In some phases, fixed tilt mounting was employed for simplicity and low maintenance. In others, single-axis tracking systems were installed, allowing panels to pivot slowly from east to west over the course of the day to capture more energy. Photovoltaic modules were lifted and positioned by crews working from specialized installation vehicles, their wiring connected in series and parallel configurations to form electrical strings. These strings fed into combiner boxes, which consolidated current before routing it through underground conduit to inverters. The inverters, housed in weatherproof enclosures, converted the direct current from the panels into alternating current, suitable for the grid. Electrical infrastructure was scaled to match the plant's increasing capacity. Transformers stepped up the voltage for transmission, and switchgear assemblies coordinated power flow to the utility interconnection point. Because of the extreme heat, electrical components were designed with thermal derating considerations, and ventilation or shading was integrated to protect sensitive equipment. Maintenance pathways were built between panel blocks, allowing access for inspection vehicles and crews. Vegetation control was minimal due to the arid climate, but the site design included erosion control measures at drainage points to protect both the panel foundations and access roads during sudden rainstorms. Rather than beginning with earthwork or bridge segments, the Patullo Bridge replacement project was first shaped by how it had to coexist with the structure it was replacing. The original bridge, a narrow steel truss span opened in 1937, needed to remain operational throughout construction. This imposed significant constraints on staging, alignment, and work zone safety, requiring meticulous sequencing and traffic management planning from the outset. The new bridge was aligned slightly upstream to minimize interference, allowing major works to proceed in parallel with live traffic. The new crossing was designed as a modern 4-lane cable-stayed bridge with provisions for eventual expansion to 6 lanes. Foundation construction began with installation of deep drilled shafts and large diameter caissons sunk into the riverbed. These elements, some exceeding 2 meters in diameter and extending dozens of meters into the underlying strata, formed the base of the bridge's main tower piers. Working in the Fraser River's dynamic flow regime meant cofferdams and silt curtains had to be used extensively to manage turbidity, prevent sediment transport, and protect aquatic habitat during pile installation and excavation. Above the waterline, the main towers were cast incrementally using climbing formwork systems. Each tower leg was built in a series of lifts, reinforced with dense rebar cages and post-tensioned anchors to resist the immense tension forces from the stay cables. These vertical elements were built with ultra-high performance concrete mixes tailored for marine exposure, freeze-thaw durability, and long-term strength gain. Cable installation followed a balanced cantilever method, where stay cables were added symmetrically from each tower to support segments of the bridge deck as they were assembled. The deck segments themselves were prefabricated off-site and barged to the location, then lifted into position using floating cranes and strand jacks mounted on temporary erection towers. As each segment was placed, its corresponding pair of cables was tensioned to support the dead load and ensure proper geometric alignment. The approach spans utilized a combination of precast and cast-in-place concrete girders supported by pile caps and column piers. These sections included integrated infrastructure for lighting, drainage, and utilities. Beneath the deck, seismic isolation bearings and expansion joints were installed to accommodate both temperature movement and earthquake-induced displacements, which were particularly important given the region's seismic profile. On land, extensive roadway realignment was undertaken on both ends of the bridge. This included new interchanges, elevated ramps, and pedestrian pathways. Utilities had to be relocated in coordination with multiple agencies, and temporary detours were constructed to keep traffic flowing during tie-in phases. Intelligent transportation systems were also built into the new alignment, including dynamic signage, cameras, and automated incident detection. A major feature of the new bridge was the incorporation of separated paths for cyclists and pedestrians, physically divided from vehicle lanes by barriers and raised decks. These facilities were not just add-ons, but integrated from the structural design phase, with loads, wind effects, and vibration behavior considered during the modeling of the full bridge system. Few infrastructure projects in the northeastern United States have so comprehensively redefined regional mobility as the construction of the Governor Mario M. Cuomo Bridge. Spanning the Hudson River between Tarrytown and Nyack, this modern twin-span structure replaced the aging Tappan Zee Bridge, which had served for over 6 decades but was increasingly unable to meet the demands of 21st century traffic, safety, and structural performance requirements. The replacement effort was not only monumental in scale, but also served as a showcase of accelerated design build execution, seismic resilience, and long-span cable-stayed bridge engineering. Construction began with an extensive program of pile driving and cofferdam installation in the river's soft glacial sediments. More than 1,000 piles were driven to create the foundations for the main span towers and approach piers, with many of them extending over 200 feet below the river surface to reach competent strata. These piles were either steel pipe piles or concrete-filled steel cylinders driven using high-capacity hydraulic hammers aboard floating barges. Each pile had to be carefully aligned to meet strict tolerances, and dynamic load testing was performed regularly to verify bearing capacity. Central to the structure are the cable-stayed main spans, each carrying 4 lanes of traffic with additional space for emergency shoulders and a shared use path. The twin main span towers, constructed with reinforced concrete, rise from pile-supported cofferdams and were built incrementally using jump form systems. These towers house the anchorages for the stay cables, which are arranged in a semi-fan configuration and composed of galvanized steel strands enclosed in protective sheathing. Each cable was tensioned individually using strand jacks, and their load paths were continuously monitored throughout installation to maintain even deck camber and prevent distortion. The bridge's deck was constructed using precast concrete panels and structural steel girders. These panels were fabricated off-site and barged to the work zone, where they were lifted into place by gantry cranes and secured with high-strength post-tensioning systems. By utilizing modular construction, the project team reduced field labor intensity and maintained strict quality control over concrete finishes and rebar placement. Simultaneously, orthotropic deck sections were integrated into specific areas where weight savings were essential, particularly near the tower anchorages. Wind loads and thermal expansion across the bridge's more than 3-mile length were key design considerations. Expansion joints with built-in damping systems were installed at each abutment and tower transition. The bridge is also equipped with smart monitoring systems embedded within its structure, capable of measuring strain, tilt, temperature, and traffic load in real time. On the western span, a dedicated bicycle and pedestrian path was constructed, complete with belvederes for scenic viewing and interpretive signage. This element, though minor in structural weight, required careful coordination with the main deck construction to maintain alignment, loading distribution, and railing continuity. The lighting system was also integrated directly into the bridge structure, minimizing the need for maintenance access while providing full spectrum LED visibility and programmable displays for special events. Across the Hackensack River in New Jersey, one of the most vital pieces of the Northeast Corridor's modernization is rapidly nearing completion. As of October 2025, construction on the Portal North Bridge is in its final phase, with the new structure scheduled to be fully operational before the end of the year. This critical megaproject replaces a century-old swing bridge that has long been a bottleneck for Amtrak and NJ Transit trains traveling between Newark and New York Penn Station. The new bridge is a fixed-span, high-level structure designed to eliminate the need for movable components, which have historically caused delays due to mechanical failures and marine openings. Unlike the aging Portal Bridge, which sits low and must pivot open for river traffic, the new Portal North Bridge provides over 50 feet of vertical clearance above mean high water, allowing commercial vessels to pass unimpeded beneath it. This design dramatically increases rail reliability by removing the risk of bridge jams and misalignments that plagued the legacy structure. Construction of the bridge superstructure involves massive steel girder assemblies placed atop reinforced concrete piers. Each pier is supported by deep foundation piles driven into the riverbed, engineered to resist horizontal river forces, wind loads, and the weight of electrified double-track rail traffic. The bridge spans more than 900 feet in total length, with its main span centered over the navigable channel of the Hackensack River. High-capacity cranes and floating work platforms have been used throughout construction to maneuver heavy steel segments and concrete deck panels into place. One of the major construction challenges tackled in 2025 involves the integration of the new bridge into the existing Northeast Corridor rail alignment. This includes grading new approach embankments, installing continuous welded rail, and connecting overhead catenary systems for uninterrupted electric train operation. Specialized track transition structures are also being finalized to minimize vibrations and ensure smooth passage for both high-speed Amtrak trains and slower NJ Transit commuter services. Signal infrastructure, positive train control equipment, and power distribution systems are being installed in tandem with track work, ensuring that the new bridge meets all federal safety and operational requirements. Additionally, flood control and drainage systems have been integrated into the approach structures to enhance the bridge's resilience to extreme weather and storm surge events increasingly common in the region. Throughout 2025, crews are also decommissioning and preparing for the removal of the existing Portal Bridge once the new structure is fully activated. This process involves isolating legacy signal circuits, rerouting services, and executing cutover operations with minimal disruption to daily rail schedules. Once open to service later in 2025, the Portal North Bridge will mark a turning point for the Northeast Corridor by eliminating one of its most notorious choke points. It will increase capacity, improve schedule reliability, and serve as a foundational element of the broader Gateway program, setting the stage for future improvements, including the Hudson Tunnel project. The new bridge represents a long-awaited investment in both regional mobility and national rail infrastructure.
In 2026, one of the most visually dramatic megaprojects under construction in San Francisco is the redevelopment of the Potrero Power Station site. Rising on a stretch of industrial waterfront in the Dogpatch neighborhood, this 29-acre site is being transformed from a rusting relic of the city's energy past into a dense, mixed-use community that blends housing, innovation space, and public waterfront access. After decades of inactivity and pollution, the area is now filled with active construction, with multiple buildings rising around the preserved smokestack that once powered large parts of San Francisco. This year marks a turning point in the project's timeline. Key infrastructure has been installed, roads are taking shape, and vertical construction is advancing on several residential and commercial buildings. The first wave of occupancy is expected in 2027, while full build-out of the project will continue into the early to mid-2030s. In terms of current construction activity, 2026 is the first year where the scale and form of the new neighborhood are clearly emerging on the skyline. The development plan includes over 2,600 residential units, 20% of which are designated as affordable, along with office space, labs, retail, cultural venues, and a massive new waterfront park. In 2026, at least 4 parcels are under active construction, with cranes on site, facades being installed, and streetscape work underway to connect the site to the surrounding Dogpatch and Pier 70 developments. The power station's original brick boiler house is being stabilized and preserved to eventually be converted into a centerpiece public building, part of a broader trend in the project to mix new construction with industrial heritage. The Potrero Power Station site has long been one of the last undeveloped pieces of San Francisco's southeastern waterfront, and in 2026, it's becoming a key node in a chain of megaprojects that are physically reconnecting the city to its shoreline. The public realm is a major focus of the construction, with waterfront promenades, plazas, and parks currently being graded and landscaped to open in stages beginning in 2028. These green spaces are designed not just for beauty, but for resilience, integrated with sea level rise protection and sustainable stormwater systems. A major portion of the site is also being prepared for future commercial tenants in the life sciences and advanced technology sectors. In 2026, lab-ready office space is under construction, with leasing expected to begin the following year. These facilities are a core part of the megaproject's economic impact, offering high-tech employment opportunities and reinforcing San Francisco's role in the Bay Area Innovation Corridor. Construction in 2026 is being carried out with strict environmental oversight, given the site's legacy as a fossil fuel power plant. Soil remediation, groundwater treatment, and air quality monitoring are ongoing as each new section of the site is prepared for development. This adds complexity, but also makes the transformation more significant, turning a brownfield into a 21st century neighborhood that meets the city's housing and sustainability goals. When fully completed, the Potrero Power Station will be a dense, transit-rich waterfront extension of the city, blending over 6 acres of parks, thousands of homes, and over 1 million square feet of office and retail space into a single cohesive community. In the landscape of San Francisco's 2026 megaprojects, it stands out for its mix of industrial past and future potential. Every structure rising here is part of a deliberate effort to reshape how cities evolve, from polluted infrastructure into vibrant, livable places.
Quite like the Portal North Bridge replacement, this vital link over the Hackensack River in New Jersey a bottleneck for both commuter and intercity rail, required a complete structural and operational transformation. The original swing-span bridge, built in the early 1900s, was not only mechanically outdated, but also posed significant operational constraints due to its low vertical clearance and movable span that had to open for marine traffic. The replacement structure addresses these issues through a fixed span design elevated high enough to accommodate river navigation without disrupting rail service. Construction began with site access improvements, including utility relocations, staging platform installation, and the construction of temporary trestles to allow cranes and materials to move efficiently across the tidal wetlands. The geotechnical profile of the area necessitated deep foundation work. Driven steel H-piles and drilled shafts were used to create load-bearing capacity within the soft riverine sediments. Vibratory hammers and impact pile drivers were employed, with real-time monitoring to reduce vibration transmission to nearby rail operations and residential structures. The new bridge structure consists of a series of through-girder spans made from weathering steel, designed to resist corrosion in the harsh marine atmosphere. Prefabricated girder segments were shipped to the site by barge, hoisted into position by floating cranes, and spliced using field-welded connections. These spans rest on reinforced concrete piers constructed using cofferdams in the riverbed. The cofferdams were dewatered, then excavated and filled with tremmy concrete to form seal slabs before pier shafts were cast in place. Reinforcement cages for the piers were assembled off-site and lowered into place using heavy lift cranes. Track systems were constructed on ballastless deck slabs using direct fixation fasteners to reduce track vibration and long-term maintenance needs. Each track was aligned to extremely tight tolerances, critical for maintaining the high-speed rail standards of the corridor. New overhead catenary systems were installed, with mast foundations constructed in parallel with the substructure work. These systems included constant tension mechanisms to accommodate thermal movement, ensuring uninterrupted power delivery to electric locomotives. To minimize service interruptions on the Northeast Corridor, much of the bridge's integration work was conducted during night and weekend outages. Existing signal and interlocking systems had to be reprogrammed, with new cabling, relay cases, and fiber connections installed alongside the structure. Signal cutovers and testing followed Federal Railroad Administration protocols to ensure full system compatibility and safety. The project also required environmental mitigation measures, especially related to aquatic habitat and wetland disturbance. Silt curtains, turbidity monitoring, and fish migration scheduling were all part of the compliance framework. Additionally, the construction team coordinated with the Coast Guard to ensure navigational access was maintained during critical phases of in-water work. In the construction of high-rise structures like the Waterline Tower, vertical integration is the principal logistical and engineering challenge. Rising tangled at the heart of Reno's freeway network, the Spaghetti Bowl has long been a nexus of intersecting routes, and the ongoing reconstruction project aims to untangle congestion while improving safety and capacity. The engineering challenge begins with phasing, keeping traffic flowing on both Interstate 80 and US Route 395, while major portions of the interchange are rebuilt. This requires carefully staged construction zones, temporary lane shifts, and a progression of work that avoids full closures wherever possible. The project involves replacing and reconfiguring multiple flyover ramps, each supported by a combination of cast-in-place reinforced concrete piers and precast concrete girders. Foundation crews first install drilled shafts deep into the underlying alluvial soils, using casing to stabilize the boreholes before placing reinforcing cages and pouring concrete. Above-ground piers are designed for both vertical load-bearing and lateral resistance to seismic forces, given the region's proximity to fault lines. One key focus is increasing ramp radii to allow smoother merges and higher design speeds. This necessitates realigning embankments and, in some cases, building entirely new bridge structures adjacent to the existing ones. Steel or pre-stressed concrete beams are delivered in segments lifted into place by large capacity cranes during nighttime closures to minimize disruption. Drainage upgrades are essential in the interchange's low points, where stormwater can collect rapidly. New catch basins, reinforced concrete pipe, and outfall structures are installed to handle runoff from both pavement and bridge decks. Erosion control measures, such as rock riprap and vegetated swales, are placed to stabilize embankments during and after construction. The project also modernizes the roadway surface itself. Existing asphalt pavement is milled away, base layers are inspected and repaired, and new lifts of high-performance asphalt or Portland cement concrete are laid down. The surface mixes are selected for durability under heavy truck traffic and resistance to freeze-thaw cycles common in northern Nevada winters. Signage, lighting, and safety barriers are also overhauled. Overhead sign structures are erected with improved sight distances, LED lighting is added for better nighttime visibility, and new concrete barrier walls are installed to meet current impact standards. Intelligent transportation system components, traffic sensors, cameras, and variable message signs are integrated to provide real-time traffic data and incident response capability. When complete, the Reno Spaghetti Bowl project will replace a decades-old interchange with a modern, higher-capacity system built to current engineering standards, improving not just traffic flow, but also safety, stormwater control, and long-term structural resilience. Rather than originating from a single excavation point, the Ontario Line subway project in Toronto is unfolding simultaneously across multiple zones, each with distinct geotechnical profiles, construction constraints, and staging challenges. This complex, phased approach is dictated by the nature of the line itself, a hybrid system incorporating underground tunnels, surface-level alignments, and elevated guideways, all within a dense urban environment with deeply entrenched infrastructure. The underground segments begin with launch shaft construction, typically established in large open-cut excavations. These shafts are stabilized with secant pile walls or soldier pile and lagging systems, supported by steel struts or tiebacks to resist lateral soil pressures. Excavation descends in stages to reach the tunnel invert elevation, where tunnel boring machines are then assembled and launched. Each TBM is equipped with an earth pressure balance or slurry shield, depending on soil conditions, allowing it to navigate soft soils, mixed face conditions, and glacial till while maintaining face stability. Tunnel lining is performed immediately behind the TBM's cutting head using precast concrete segments. These segments are gasketed and bolted to form a watertight ring, which becomes part of the permanent tunnel structure. The logistics of segment delivery, spoil removal, and TBM maintenance are coordinated from surface-level support sites, which include slurry processing plants, muck storage, and concrete casting yards. At intermodal stations like Exhibition, Osgood, and Queen, massive excavation pits are established using a top-down or cut-and-cover method. These stations interface with existing subway lines and utility corridors, necessitating complex underpinning of adjacent buildings, and the use of ground freezing or jet grouting to control groundwater inflow. Temporary decking allows surface roads to remain operational while deep excavation continues below. Internal strutting systems are critical to maintain the integrity of the excavation, particularly for multi-level station boxes with mechanical, ventilation, and emergency egress spaces. Above ground, elevated guideways are constructed using precast segmental construction or cast-in-place concrete methods. These viaducts require column piers with deep foundations, often drilled caissons or driven piles, to ensure stability in areas with compressible soils or fluctuating groundwater. Segments are lifted using launching gantries or segment lifters, then post-tensioned together to form continuous spans. Alignment tolerances are extremely tight to maintain ride quality and track geometry. Track installation across the entire line incorporates both direct fixation systems and traditional ballast and tie methods, depending on location. In tunnels, low-vibration track slabs are installed using high-strength concrete over a waterproofed base. Track work includes rail anchors, expansion joints, and insulated rail fasteners, all designed to meet noise, vibration, and thermal movement requirements. A substantial portion of the Ontario Line's complexity comes from its integration with live transit corridors, roadways, and utility networks. This involves ongoing utility relocations, including water mains, high-voltage cables, and telecommunications lines, all done with extensive traffic staging and night shifts to reduce surface disruptions. Monitoring of existing structures is continuous, using inclinometers, strain gauges, and real-time survey systems to detect any movement induced by construction activities. In an environment where minimizing disruption to major interstate corridors is paramount, the I-95 bridge replacement in Westport, Connecticut, demonstrated the full potential of accelerated bridge construction methods, specifically the lateral slide technique. This project involved replacing a structurally deficient bridge over Saugatuck Avenue, one of the busiest stretches of I-95 in the region, and doing so within a matter of days rather than months. The strategy required meticulous preparation, extensive off-site construction, and flawless execution during a very short highway closure window. The existing structure, carrying both northbound and southbound traffic, had reached the end of its service life. Deterioration in the substructure and deck made full replacement necessary, but the surrounding context, a dense suburban area with no practical detour options, meant that a traditional replacement approach was unfeasible. Engineers turned to a plan that would pre-build the new bridge spans adjacent to the existing alignment, then slide them into position during a single, carefully scheduled weekend closure of I-95. Before anything could be moved, a complex network of temporary supports, approach transitions, and hydraulic jacking systems had to be prepared. Construction crews built the new bridge structures on temporary foundations parallel to the active highway lanes. These new spans consisted of precast concrete deck panels integrated with steel girders, forming a composite superstructure. All connections, reinforcements, drainage components, and lighting conduits were pre-installed to reduce on-site finishing work after the move. While traffic continued to flow on the existing bridge, crews below worked on the new bridge's final foundation and abutment construction. These included concrete abutments supported by deep foundation systems, such as driven piles, along with bearing pads designed specifically to accept the sliding load. The horizontal slide surface was engineered using Teflon-coated pads and stainless steel slide tracks designed to minimize friction during the move. When the designated closure window arrived, the entire section of I-95 was shut down, and demolition crews moved quickly to remove the existing bridge. This required heavy excavators, saw-cutting equipment, and debris haulers working in synchronized shifts to clear the area within hours. As soon as the old structure was out of the way, hydraulic jacks were engaged to push the new bridge spans laterally onto the permanent abutments. This slide was conducted at a controlled pace, typically a few feet per hour, with continuous monitoring to ensure alignment, levelness, and bearing engagement. Once the new bridge was in place, the final phase included forming and pouring the deck closure joints, completing the approach slabs, connecting utility runs, applying waterproofing membranes, and finishing the surface paving. Precast parapets and guardrails were already attached to the new deck, eliminating the need for extensive post-move safety installations. Within just a few days, traffic was flowing again over a brand new structure with enhanced load capacity, seismic performance, and modern safety features. The I-95 bridge slide in Westport became a prime example of how advanced construction methods can be leveraged to perform full-scale bridge replacements in compressed timelines without sacrificing quality, safety, or functionality. Deep beneath the streets of Baltimore, as of October 2025, tunnel boring operations and civil construction continue in earnest on the Frederick Douglass Tunnel project, a transformative upgrade to one of the most critical bottlenecks on the Northeast Corridor. Designed to replace the aging B and P tunnel, which dates back to the post-Civil War era, the new Frederick Douglass Tunnel is on track for completion by the end of 2025 and will significantly improve rail capacity, reliability, and safety through one of the NEC's most congested segments. The project consists of a new twin-bore tunnel alignment, each tube roughly 2 miles in length, and excavated using massive tunnel boring machines designed specifically for the challenging geotechnical conditions beneath West Baltimore. The soils encountered range from clayey silt to weathered rock, requiring variable density TBMs capable of managing ground pressure fluctuations while maintaining precise alignment tolerances. The inner diameter of each tunnel is large enough to accommodate electrified double-track rail systems, built with long-life precast concrete tunnel lining segments bolted and grouted in place behind the TBM shield. To support tunnel operations and eventual service integration, multiple ancillary structures are under construction along the alignment. These include ventilation buildings, emergency egress shafts, and utility relocation corridors, all built to current National Fire Protection Association 130 standards for passenger rail tunnels. High-capacity fans and HVAC systems are installed within the ventilation shafts to ensure smoke control and air quality management in case of emergencies. Access points are strategically located to support future maintenance without interrupting service. Rail infrastructure installation is another focus of 2025 activities. Crews are installing continuously welded rail on resilient trackbed systems designed for high-speed operation, with ballastless track slabs in the tunnel sections for smooth, low-maintenance performance. Electrification systems, including overhead catenary, traction power substations, and signal infrastructure, are being placed in coordination with Amtrak and MER, HARAC system requirements. Special attention is paid to integration with positive train control and modern signaling systems, which will allow for higher throughput and improved timetable precision across the corridor. At both ends of the tunnel, extensive surface work is being carried out to tie the new tunnel into existing NEC infrastructure. This includes regrading track approaches, reconfiguring interlockings, and constructing new portal structures with drainage systems engineered to handle flash flooding events. Bridge work and utility diversions are being finalized as part of the portal area reconstruction, with minimum service disruption maintained through staged construction and temporary track shifts.
Buried beneath the surface of San Francisco's downtown in 2026 is one of the city's most consequential megaprojects under construction, the Portal, also known as the Downtown Rail Extension. This massive underground infrastructure project is finally being realized after decades of delays, aiming to connect Caltrain and eventually California's high-speed rail directly to the Salesforce Transit Center. As of this year, excavation work is ramping up, tunneling contracts are active, and the city is fully committed to completing the extension by the early 2030s. In 2026, the Portal is a hive of subterranean activity. Tunnel boring preparations are in progress, utility relocation is underway, and major downtown streets are experiencing stage disruptions as crews create access points for the underground guideways. It's one of the most complex transportation builds in the Bay Area, requiring coordination beneath some of the densest blocks in the city. Once complete, this megaproject will deliver a seamless rail connection from the peninsula and Central Valley straight into the financial core of San Francisco. The project involves building approximately 1.3 miles of new track, mostly underground, to link the existing Caltrain line near 4th and King with the Salesforce Transit Center. In 2026, the staging areas at both ends of the project are fully operational. Pile driving, shoring walls, and structural reinforcements are all happening in real time as the city begins to carve out the physical corridor that will carry thousands of passengers daily. Construction in and around Townsend, 2nd Street, and the south of Market area is active and accelerating, with visible impacts above ground and substantial progress being made below it. The portal isn't just a rail project, it's a regional unlock. In 2026, Caltrain still terminates at 4th and King, about a mile short of downtown. That last mile has long been the missing link in Bay Area transit. By closing that gap, this project will plug regional rail directly into San Francisco's business core, reducing car dependency and reshaping how people move across the region. When complete, the portal will allow Caltrain riders to disembark in the heart of the city and will set the stage for future high-speed rail service to run directly from Los Angeles to downtown San Francisco, without transfers. The current timeline targets a completion date in the early 2030s, with most heavy construction expected to occur between 2026 and 2030. In the context of San Francisco's other megaprojects under construction right now, the portal stands out for its invisibility. Most of the work is happening underground, but the scale of its impact will rival that of any tower or waterfront redevelopment. Cost is high, risk is real, and coordination is intense. Crews are navigating under live utilities, major foundations, and transit lines. Every foot of tunnel requires precision, and every stage of construction must account for seismic resilience, waterproofing, and integration with existing BART and MUNI infrastructure. In 2026, engineering teams are deep into geotechnical work and soil stabilization, preparing for the eventual tunnel boring operations that will begin in earnest in 2027.
Like the Puget Sound Gateway involves more than just building new roadways. It is about stitching together ports, distribution centers, industrial zones, and population centers with a network designed to withstand decades of growth and geotechnical complexity. The program hinges on completing two major corridor extensions, State Route 167 to the Port of Tacoma and State Route 509 to the Seattle-Tacoma International Airport area. These aren't simple highway extensions. They are multifaceted infrastructure systems woven through dense urban fabrics, environmentally sensitive zones, and active logistics corridors. The foundational effort began with extensive right-of-way acquisition, including dozens of industrial parcels, commercial lots, and sections of public land. Site clearing and demolition work had to be carefully sequenced to ensure active businesses and transportation flows weren't unduly disrupted. In many areas, phased demolition and temporary access roads were used to maintain traffic and construction staging efficiency. Once the sites were cleared, earthwork operations commenced with mass excavation, grading, and fill operations to establish the subgrade profiles for the new alignments. These activities often encountered unstable soils, particularly in areas near water bodies and wetlands, necessitating ground improvement methods such as stone columns, surcharge embankments, and wick drains to accelerate consolidation and avoid long-term settlement. Bridges form a central component of the Puget Sound Gateway's design, given the number of water crossings, rail corridors, and urban arterials the new routes must span. Structural systems varied by location. Some employed pre-tensioned concrete girders, while others utilized steel box girders to achieve longer spans or accommodate vertical clearance constraints. Foundations for these bridges were built using large-diameter drilled shafts socketed into glacial till or bedrock, with temporary casings and slurry techniques used where groundwater intrusion was significant. False work systems were installed with minimal encroachment on adjacent rail and road corridors, often during tight nighttime closures, coordinated months in advance. Stormwater infrastructure was a major focus throughout the corridor. Given the region's high rainfall and environmental sensitivity, Advanced drainage systems were installed, including biofiltration swales, detention vaults, and oil water separators. In several segments, retrofits were made to older outfalls to meet updated stormwater discharge criteria. To further offset environmental impacts, the program incorporated significant wetland mitigation and stream restoration work. This included regrading stream beds, planting native vegetation, and installing fish-passable culverts to enhance salmon habitat connectivity. The roadways themselves were built with high modulus asphalt pavement sections capable of handling repeated heavy truckloads. Base layers were constructed using crushed aggregate wrapped in geotextile fabric to separate the subgrade from the structural layers. Intelligent transportation systems were installed throughout the new corridor sections, with fiber optic cabling laid in trench alongside the roadbeds to support variable message signs, CCTV, incident detection, and traffic management. Logistics were further complicated by the need to interface with ongoing freight rail operations and existing intermodal yards. Coordination with railroads was critical, especially during the construction of new overpasses and underpasses, where flagging operations, temporary shoring, and phased construction minimized service interruptions. Few infrastructure projects in the Northeast Corridor combined century-old obsolescence with 21st century engineering demands. Vegas Strip, the T-Mobile Arena was conceived as a multi-purpose venue capable of hosting everything from championship hockey to high-profile concerts. Its construction demanded a compact, vertical approach to fit within the limited site footprint, while still accommodating seating for tens of thousands of spectators. Engineers began with a deep excavation for the foundation, where reinforced concrete pile caps and spread footings supported the load of the superstructure. The subgrade preparation included soil stabilization measures to counteract any settlement in the alluvial deposits common in the area. The arena's structural system is a hybrid of reinforced concrete for the lower bowl and steel framing for the upper tiers and roof. Massive steel trusses were fabricated off-site, then transported in segments and lifted into position using crawler cranes with high lifting capacities. These trusses form the backbone of the long-span roof, which was designed to eliminate interior columns that could obstruct views. The roof decking incorporated acoustic insulation and energy-efficient membranes to regulate interior climate and reduce noise transmission. Exterior cladding was chosen both for aesthetics and thermal performance. The facade combines glass curtain walls, metal panels, and shading fins to break up the building's mass while controlling solar gain. The curtain wall system was engineered to withstand high wind loads while maintaining clarity and transparency, allowing the glow of interior lighting to become part of the strip's nighttime skyline. Inside, the seating bowl was designed with steep rakes and precisely calculated sightlines to keep spectators close to the action. Concrete risers and precast seating elements were installed in phases, coordinated with mechanical, electrical, and plumbing rough-ins that run beneath the concourse floors. The MEP systems themselves were scaled to handle large surges in occupancy, with high-capacity HVAC units, robust fire suppression systems, and redundancy in electrical feeds to maintain operations during events. One of the more complex phases involved installing the event flooring systems. For ice hockey, a network of embedded refrigeration pipes circulates glycol solution beneath the slab, allowing rapid ice formation. For concerts or basketball, modular floor panels cover and protect the ice while providing a stable surface for staging. The final phase focused on integrating technology and finishes. Advanced LED ribbon boards, a high-definition center-hung scoreboard, and distributed audio systems were installed alongside premium seating areas, luxury suites, and public concourses finished with durable, easy-to-maintain materials. When completed, the T-Mobile Arena became not just a venue, but a highly engineered piece of infrastructure designed for flexibility, efficiency, and the high demands of Las Vegas' non-stop entertainment environment. Beneath the water overlooking the Peace River in northeastern British Columbia, the Site C Dam emerged as the third major hydroelectric development on this river, following the Wack Bennett and Peace Canyon dams. Planning for this project involved decades of studies, regulatory reviews, and public consultation before actual construction began in the mid-2010s. Once approved, the first phase of construction focused on site clearing and access preparation. This entailed removing thousands of hectares of vegetation, felling trees, building new access roads, and reinforcing existing ones to accommodate the massive flow of equipment and personnel. Additionally, geotechnical investigations were carried out early to determine subsurface characteristics, which were critical for designing stable foundations in a valley known for its complex geological conditions. Foundation excavation proceeded next, with crews stripping away overburden to expose competent bedrock. This phase involved the use of heavy earth-moving equipment such as hydraulic excavators, bulldozers, and articulated dump trucks, operating on a meticulously choreographed schedule to avoid bottlenecks. Extensive rock bolting and grouting were performed to stabilize the slopes and ensure that water seepage through the foundation would remain within allowable limits. At the same time, river diversion tunnels were being bored through the north bank. These twin tunnels, each several hundred meters long and several meters in diameter, were lined with reinforced concrete and designed to carry the full volume of the Peace River during the dam's construction phase. Once river diversion was in place, the main earth-fill dam structure began to take form. This embankment-type dam required the placement of millions of cubic meters of material in zoned layers, each serving a specific structural or impermeable function. The dam's core consisted of compacted clay designed to be nearly watertight, while the outer shells were built from gravel and rockfill for strength and stability. These layers had to be placed with extreme precision, both in terms of moisture content and compaction density, using a fleet of high-capacity vibratory rollers and GPS-guided dozers. Simultaneously, the powerhouse and spillway complex were under construction on the left bank. These concrete structures demanded an entirely different set of construction techniques, beginning with the erection of massive cofferdams to dewater the work area. Tremie concrete was often used for underwater placements, while large tower cranes and high-capacity formwork systems enabled continuous vertical construction. The powerhouse was designed to house 6 large Francis-type turbine generator units, each requiring massive steel components that were fabricated off-site and transported in modules. Beyond the physical structures, a network of transmission lines was installed to carry the electricity generated at Site C to the provincial grid. These high-voltage lines required the erection of steel lattice towers across challenging terrain with careful coordination to avoid environmental and cultural sensitivities. Environmental mitigation was a persistent theme across all stages of the project, involving fish habitat reconstruction, wildlife corridor planning, and ongoing monitoring of water quality and sediment levels. Unlike traditional infrastructure projects that begin with roads and utilities, the Atlantic Spaceport complex in Newfoundland and Labrador began with a deep analysis of coastal wind patterns, azimuth corridors, and orbital trajectories. The remote coastal site was selected specifically for its unobstructed access to polar and sun-synchronous orbits, as well as its low population density and relatively stable geology. This strategic positioning allowed for near-direct launch windows without complex flight path maneuvers, reducing both fuel requirements and orbital insertion complexity. The first stages of construction involved establishing the core operational footprint, clearing and grading vast tracts of rugged terrain while maintaining strict environmental control protocols. The subarctic climate and sensitive coastal ecosystems meant erosion control and sediment filtration systems had to be installed from the outset. This included silt fencing, drainage swales, and retention ponds strategically placed to intercept runoff from access road construction and earth-moving operations. Foundations for key facilities were drilled and anchored into the underlying bedrock, with special focus on the vertical launch platform and flame trench system. The launch pad itself was built atop a reinforced concrete slab capable of withstanding the immense thermal and vibrational loads produced during ignition. Underneath, a flame trench with diverging deflectors was cast in place using high-temperature refractory concrete designed to channel exhaust gases laterally and away from sensitive infrastructure. Adjacent to the pad, the integration facility was constructed using a pre-engineered steel frame building with overhead cranes rated for high-capacity vertical payload handling. This structure houses the vehicle assembly bay, clean rooms for payload encapsulation, and support areas for avionics checks, fueling operations, and pre-launch verification. The integration building was situated on vibration-isolated pads and includes anti-static flooring, air filtration systems, and redundant HVAC to maintain strict contamination control for orbital payloads. Fuel storage infrastructure, often a critical element of launch safety, was developed in a separate blast-buffered zone. This area includes cryogenic liquid oxygen tanks, kerosene or methane fuel silos, and purge gas systems, all with multi-layered spill containment and automated fire suppression systems. Pipelines connecting the storage yard to the launch pad were installed below grade within concrete service trenches, incorporating emergency shutoff valves and leak detection instrumentation. A specialized telemetry and tracking station was also established early in the project, featuring radar arrays, satellite uplinks, and optical tracking mounts positioned on elevated piers to ensure line of sight during all launch phases. Fiber optic data lines were buried in hardened conduits, linking this station directly to the Mission Control Center and external ground station networks. Power systems across the complex were backed up with dual redundant generators and uninterruptible power supplies to maintain continuity during critical countdown sequences. Access roads were widened and paved to accommodate heavy launch vehicle components delivered via modular transporters. Additionally, a barge landing site was constructed to facilitate oversized cargo deliveries via sea, with a reinforced quay wall and mooring points integrated into the coastal rock face. Beneath the southern skyline of Portland, Oregon, the Sellwood Bridge replacement project unfolded as a carefully orchestrated effort to modernize a century-old crossing while respecting the constraints of an urban setting and a sensitive river environment. Originally opened in 1925, the existing structure had long been structurally deficient and functionally obsolete. It carried tens of thousands of vehicles per day on a narrow, deteriorating deck with no shoulders and minimal pedestrian accommodations. The new bridge would not only replace the failing structure, but also vastly improve safety, seismic resilience, and multimodal capacity. The design of the replacement bridge called for a deck arch structure which would span the Willamette River with minimal disruption to the waterway and surrounding neighborhoods. Prior to any new construction, engineers faced the unique challenge of what to do with the existing bridge. Instead of fully demolishing it up front, a temporary solution was implemented. The original steel truss was shifted laterally, intact, onto temporary piers constructed just downstream. This extraordinary lateral slide operation allowed the old bridge to remain in service while the new bridge was built in its original alignment. The lateral move required precise hydraulic jacking systems and heavy-duty rollers. Crews disconnected the truss from its existing piers and then slowly slid the entire structure onto a set of temporary supports built on drilled shafts. This move, executed in just a few hours after weeks of preparation, cleared the path for demolition of the original concrete piers, many of which had suffered extensive corrosion and were no longer structurally viable. With the original alignment clear, construction of the new bridge began with installation of deep foundation elements, including drilled shafts socketed into bedrock beneath the riverbed. These shafts would support the new reinforced concrete piers, which in turn carried the load of the deck arch. The arch segments were constructed using a balanced cantilever method, with concrete segments cast in place and post-tension to maintain structural integrity as they extended symmetrically from each side of the river. The bridge deck itself was cast in segments atop the arch ribs using a system of falsework and custom-formed travelers. The deck accommodated 2 standard travel lanes in each direction, generous bike lanes, and wide sidewalks on both sides, features entirely absent from the original structure. In addition, the deck design included integrated stormwater treatment systems to capture and filter runoff before it entered the Willamette River. As the new bridge took shape, utilities were relocated, traffic patterns shifted, and seismic isolators were installed beneath critical components to provide flexibility in the event of an earthquake. Steel reinforcement was designed with corrosion resistance in mind, and all concrete elements were specified with admixtures tailored to the region's wet climate. Once the new structure was complete and fully operational, the old temporary bridge was dismantled and removed from its temporary supports. Final phases included landscaping, approach road improvements, and installation of aesthetic lighting and railing features to blend the bridge with its urban and natural context. What sets the Champlain Hudson Power Express apart in the landscape of US infrastructure projects is not just its scope, but the subterranean and subaquatic nature of its entire path. As of October 2025, construction is entering its final phase, with full system completion targeted by the end of this year. This high-voltage direct current transmission line is designed to carry up to 1,200 megawatts of renewable hydroelectric power from Quebec directly into New York City, helping the state meet its aggressive decarbonization goals. The total route spans approximately 339 miles from the Canadian border near the town of Champlain, New York, down to a newly constructed converter station in Astoria, Queens. Unlike most overhead transmission projects, nearly the entire length of the Champlain Hudson Power Express is buried, either beneath existing transportation corridors or submerged under bodies of water such as Lake Champlain and the Hudson River. This underground design dramatically reduces visual impact, simplifies permitting in populated areas, and adds protection against extreme weather events. In terms of construction methodology, the project employs horizontal directional drilling, trenchless burial, and hydroplow installation techniques depending on terrain type. Underwater segments are placed using barge-mounted equipment that can lay cable along pre-surveyed paths on lake or riverbeds. Specialized hydroplow systems simultaneously trench and embed the cable in sediment, using pressurized water to create a narrow channel before backfilling it naturally. On land, where the cable parallels roadways and rail lines, teams use HDD rigs to tunnel beneath sensitive crossings, preserving existing infrastructure above. Each of the HVDC cables, positive and negative conductors, are sheathed in layers of insulation, shielding, and armoring to protect them from physical damage and electrical faults. These cables are manufactured in continuous lengths that can reach over 3 miles, requiring precise logistics coordination to transport, coil, and unwind them during installation. Cable joints are made in weather-controlled enclosures, and each connection undergoes rigorous partial discharge and high-voltage testing before being backfilled and reburied. The converter station at the southern end in Queens serves as the electrical interface where direct current is converted back into alternating current for integration into the New York Independent System Operator Grid. This facility includes modular multi-level converters, advanced cooling systems, harmonic filtering equipment, and extensive control automation to maintain voltage stability and synchronization with the regional grid. In 2025, final phases of construction include completion of remaining landfall segments, full systems testing, and final commissioning of both converter stations. Environmental monitoring and cable protection measures are also being finalized to ensure long-term reliability and compliance with state and federal regulations. With commercial operation anticipated by the end of 2025, the Champlain-Hudson Power Express will stand as one of the longest underground transmission lines in North America. Its delivery of clean hydropower to one of the most energy-intensive urban centers in the country represents a transformative milestone in the effort to modernize US energy infrastructure and reduce reliance on fossil fuel generation.
The Mission Rock project is one of San Francisco's headline megaprojects under active construction in 2026. Sitting directly south of Oracle Park, on what was once a windswept sea of asphalt and overflow parking lots, this 28-acre waterfront site is being turned into a dense, walkable neighborhood that combines housing, parks, offices, and retail in one of the most high-profile real estate efforts in the city. In 2026, the project is deep in Phase 1 construction. Several major buildings have already topped out, with exterior work wrapping up and interior build-outs ongoing. Full completion of this phase is expected by late 2027. When finished, it will include nearly 1,200 new residential units, over 400 of which are permanently affordable, along with 8 acres of new public space and over 200,000 square feet of office and retail space. This megaproject isn't just reshaping a site, it's helping to redefine the southern edge of San Francisco's downtown. New streets and pedestrian promenades are already being laid out, stitched together by green infrastructure and open-air plazas designed to absorb stormwater and resist sea level rise. The waterfront park, known as China Basin Park, is being built in tandem with the buildings around it. Crews in 2026 are currently sculpting the park's shoreline and planting native vegetation, with major portions set to open by 2028. Mission Rock is a public-private partnership between the San Francisco Giants and the Port of San Francisco, and the construction in 2026 reflects a long-term vision to extend the city's core outward along the waterfront. Designed as a high-density, low-emissions community, every new structure is being built to LEED Gold or higher standards. Solar panels, all-electric systems, and smart energy grids are standard here, not just features. One of the project's architectural landmarks now under construction is the Canyon, a massive mixed-use building that blends market-rate apartments with carved terraces and retail space. In 2026, the Canyon's facade is nearly complete, and interior work is progressing toward a mid-2027 delivery. Nearby, a life sciences tower being built for the biotech sector is rising quickly, with tenants expected to begin occupancy by late 2028. What makes Mission Rock such a key part of San Francisco's 2026 megaproject landscape is its fusion of uses and its central location. Unlike isolated developments on the city's edges, this project plugs directly into the transit network and urban fabric. It's within walking distance of downtown, BART, Caltrain, and multiple Muni lines. Its completion will not only provide urgently needed housing, it will expand the city's job base and public amenities in a place long dominated by underused land. As of 2026, the construction site is a hive of activity. Steel framing, glazing, mechanical installation, and hardscape development are all occurring simultaneously across multiple parcels. Each building is being developed by a different architectural team, resulting in a diversity of forms and styles that break from the monolithic look of some other megaprojects. This is intentional. Mission Rock is designed to feel like a neighborhood, not a master plan. The entire project is expected to wrap up in multiple phases through the early 2030s, with new parcels starting construction as others finish. By the time it's fully built out, Mission Rock will include 8 acres of parks, up to 1.4 million square feet of commercial space, and space for thousands of new residents.
The heart of the Link US Transit Corridors initiative is the task of transforming key transportation arteries in the Columbus, Ohio metropolitan region into high-capacity, multimodal corridors built for future urban growth. Unlike typical bus transit upgrades, the Link US program requires a comprehensive re-engineering of the roadway environment to support bus, rapid transit systems, pedestrian-focused infrastructure, and mixed-use urban development, all while preserving functionality for existing traffic and utility services. The first phase of physical work along a corridor typically involves relocation of utilities, both above and below ground. Electrical vaults, telecommunications ducts, gas lines, and water mains are mapped, protected, or moved to ensure that dedicated BRT lanes, new medians, and expanded sidewalks can be constructed without interference. In many cases, trenchless methods like horizontal directional drilling are employed to install new conduits beneath existing infrastructure with minimal surface disruption, particularly in dense commercial zones. Once the underground conflicts are cleared, road reconstruction begins. The new BRT lanes, often located in the center of the roadway, are built with reinforced concrete pavement sections designed for heavy axle loads and continuous operation. These lanes are separated from general traffic by raised curbs or delineators and incorporate mountable transitions at intersections to allow emergency access. Drainage patterns are revised through the addition of new catch basins, bioretention swales, and subsurface infiltration trenches, which both control runoff and improve stormwater quality. Platforms for BRT stations are constructed as raised, ADA-accessible boarding zones with tactile strips, real-time signage pylons, lighting, and weather shelters. Each station integrates with sidewalk improvements and signalized crosswalks, often requiring curb realignments and installation of new traffic signals with transit signal priority features. Median-based stations include special design considerations for pedestrian access, often requiring median refugees or fully protected intersection phases to ensure safe crossing movements. Beyond the roadway and platform work, the corridors also undergo significant landscape and urban design transformation. Utility pole removal, replacement of overhead wires with underground systems, and installation of street trees and furniture all contribute to a more pedestrian-oriented environment. Road diets are implemented in segments to reduce the number of general-purpose lanes, providing the right-of-way for wider sidewalks, cycle tracks, and designated turn lanes. These changes are reinforced with textured or colored pavement treatments at crosswalks and intersections to enhance visibility and reinforce multimodal priority. The Link US program also incorporates transit-oriented development zones adjacent to high ridership stops. Construction work in these areas involves coordination with private developers, staging of future utility corridors, and the preparation of building pads with coordinated grading and stormwater infrastructure. Each segment includes provisions for utilities and services. On a site with existing grid interconnections, the Reed-Gardner Battery Energy Storage System is designed to operate as a high-capacity, utility-scale installation capable of storing and dispatching electricity with rapid response times. The project began with site preparation that accounted for both structural loading and environmental considerations. Grading crews leveled the area to accommodate containerized battery units, access lanes for maintenance vehicles, and dedicated transformer and inverter pads. The subsurface was compacted and, where necessary, reinforced with aggregate base to provide a stable platform for heavy equipment placement. The storage system uses modular enclosures, often in the form of prefabricated steel containers that house the battery cells, thermal management equipment, and control electronics. Each container sits on a reinforced concrete pad equipped with embedded conduits for both power and data connections. The battery chemistry, typically lithium-ion for this type of project, is arranged in racks with integrated battery management systems to monitor voltage, temperature, and state of charge for each module. Thermal control is a critical engineering component. Given Nevada's high summer temperatures, Each container includes dedicated HVAC units and ventilation systems to keep the batteries within optimal operating ranges, preventing thermal runaway and prolonging service life. These systems are sized for redundancy, ensuring that a single failure does not compromise the integrity of the battery bank. Power conversion is handled by utility-scale inverters positioned adjacent to the battery units. These inverters transform the direct current from the batteries into alternating current synchronized with the grid. Step-up transformers then raise the voltage to match the transmission network, and protective relays and switchgear safeguard the system against faults or abnormal operating conditions. Integration with the existing substation infrastructure at the Reed Gardner site required precise electrical engineering. Relay coordination studies, short-circuit analyses, and load flow modeling ensured that the battery system could seamlessly charge during periods of low demand and discharge during peak demand without destabilizing the grid. Control systems provide automated dispatch based on real-time conditions, with the capability for remote operation by the utility's Energy Management Center. Safety considerations shaped much of the design. Fire detection and suppression systems were installed within each enclosure, along with gas detection sensors and emergency shutoff mechanisms. Clear access routes and separation distances between units reduce the risk of fire propagation. When commissioned, the Reed Gardner Battery Energy Storage System became a strategically located asset, capable of smoothing renewable generation variability, providing frequency regulation, and supporting grid reliability during demand spikes, all built on a foundation engineered for durability, safety, and long-term performance in a challenging desert climate. Stretching across thousands of acres in Story County, rather than beginning at a central hub or urban terminal, the Alto high-speed rail project's earliest fieldwork concentrated on corridor preparation through rural and semi-rural regions, where right-of-way acquisition and grading could proceed with minimal disruption. The rail line, intended to connect Toronto to Quebec City with ultra-fast, electrified service, required the creation of an entirely new grade-separated alignment, distinct from the existing freight-heavy rail network. This demanded comprehensive land surveying, geotechnical assessments, and environmental clearances across hundreds of kilometers before any civil works could start. Once alignment studies and land procurement were finalized, the corridor was divided into construction segments managed by multiple contractors. Earthworks commenced almost simultaneously across numerous stretches, involving topsoil stripping, subgrade stabilization, and extensive cut and fill operations. In some areas, embankments rose over 10 meters high to maintain consistent gradient profiles, while in others, deep rock cuts were blasted to maintain design speed tolerances. Where the route intersected natural waterways or wetlands, precast culverts and multi-span bridges were installed, with sediment control measures and wildlife passages integrated into the design. One of the most technically demanding aspects was the track bed itself. High-speed rail demands extremely tight tolerances for vertical and horizontal alignment, necessitating a multi-layered track foundation system. Sub-ballast and ballast layers were placed over geotextile reinforced subgrades compacted to precise densities. In critical high-speed segments, especially on long straightaways or gentle curves, slab track systems were used instead of ballast, incorporating precast concrete panels anchored to reinforced concrete bases. These sections offered better long-term stability and reduced maintenance frequency, essential for sustaining speeds approaching 300 kilometers per hour. Electrification followed closely behind track installation. Overhead, catenary systems were constructed using regularly spaced mass, tensioning assemblies, and contact wire supports calibrated to minimize sway and maintain constant contact with the pantograph. Substations were placed at strategic intervals to step down transmission voltage and feed it into the overhead system. These were built on elevated pads, and connected to regional grids through buried or overhead transmission lines, depending on terrain and corridor width. Stations along the Alto line featured a combination of central platform and side platform configurations, with full-length canopies, soundproofed glass walls, and automatic platform screen doors. Structures were built using steel frames and precast concrete panels to accelerate construction schedules and standardize elements across cities. At major urban terminals, such as Montreal and Ottawa, new underground concourses and connection tunnels were excavated using a mix of cut and cover and tunnel boring techniques to integrate with existing transit networks. Control and signaling infrastructure represented a core component of the system's operational integrity. The Alto line uses a European train control system adapted for Canadian conditions, relying on continuous communication between trains and trackside balises to manage speed, spacing, and braking curves. Fiber optic cables were laid alongside the right-of-way, bundled with power and data conduits in armored ducts, and routed through centralized equipment rooms for resilience and redundancy. Noise mitigation was essential throughout populated areas. This was addressed through the installation of acoustic barriers, vibration-isolated track beds, and embankment berms shaped to deflect sound. In addition, crossing eliminations were carried out at every road and rail interface, either through overpasses, underpasses, or full-grade separations, ensuring uninterrupted operation of the high-speed network. Unlike conventional bridge construction that relies on in-place assembly over active roadways, the 2nd Avenue Bridge replacement over I-94 in Detroit took a bold and modern approach, building the entire structure off-site and moving it into position in a single, coordinated operation. This method, known as self-propelled modular transport, allowed engineers to reduce highway closures dramatically while executing a highly complex structural replacement with precision and control. The original 2nd Avenue Bridge was a narrow, outdated crossing that no longer met the safety or capacity standards required for urban connectivity in the Midtown Detroit corridor. With the ongoing modernization of the I-94 freeway, it became essential to not only replace the bridge, but to do so in a way that minimized impacts to one of the busiest traffic arteries in the state. Traditional staged construction would have required extended lane closures, ongoing detours, and multiple phases spread out over months or even years. Instead, the project team designed a new, wider bridge structure that would be constructed entirely adjacent to the interstate in a staging area. This new structure, composed of steel plate girders and a concrete deck, was built on temporary supports known as false-work towers. The substructure, comprising abutments and approach walls, was prepared well in advance at the final bridge site using cast-in-place concrete supported on deep foundations, including driven H-piles embedded into firm strata beneath the interstate. Once the off-site construction was complete and all systems verified, the move operation was scheduled for a carefully planned weekend closure of I-94. The actual bridge move was performed using SPMTs, multi-axle, computer-controlled transport platforms capable of lifting and carrying massive loads with millimeter-level accuracy. The entire superstructure was lifted off its temporary falsework supports using hydraulic jacks integrated into the SPMTs. The system then slowly transported the bridge across the staging area, maneuvering over prepared access paths and aligning itself precisely with the final bridge bearings. During this process, crews on site continuously monitored bearing alignment, elevation, and lateral position, ensuring the bridge matched its abutment seat locations exactly. Once the bridge was in final position, it was slowly lowered onto elastomeric bearings, and mechanical connections were secured to tie the structure into the existing roadway network. The final stages of the operation included backfilling approach zones, paving transitions, and installing barriers and utilities, all tasks that had been prepared in advance to accelerate reopening. One major advantage of this move-in-place approach was that it compressed months of disruptive work into a matter of days. Rather than subjecting the corridor to prolonged construction noise, lane reductions, and detours, the SPMT method enabled a near instantaneous installation with minimal long-term disruption. Running beneath the dense urban fabric of East Harlem, Phase 2 of the 2nd Avenue subway is one of the most technically intricate urban transit projects underway in the United States. As of October 2025, construction is in full swing and on schedule to reach major milestones before the end of the year. This expansion of the Q line represents the continuation of a century-old vision to bring rapid transit to Manhattan's East Side, long underserved by existing subway infrastructure. Phase 2 extends the 2nd Avenue subway from its current terminus at 96th Street up to 125th Street, adding nearly 2 miles of twin-track tunnel and 3 new stations at 106th, 116th, and 125th Streets. This segment weaves through a tightly packed corridor of existing utilities, aging infrastructure, and high pedestrian activity, requiring highly controlled construction staging, deep excavation techniques, and continuous coordination with adjacent buildings and streets. Tunnel boring for the new alignment began with launch shafts excavated at key staging zones, where tunnel boring machines were assembled and driven northward through bedrock. Each TBM is designed to cut through Manhattan schist while installing precast concrete segmental linings behind the cutter head. These linings are sealed with waterproof gaskets and reinforced to resist ground pressure, seismic events, and hydrostatic loads from surrounding groundwater. Beyond tunneling, much of the focus in 2025 is on the deep station caverns. These stations are being mined and constructed up to 100 feet below street level, with complex support of excavation systems in place to stabilize the surrounding soil and protect existing buildings. Massive headhouses at street level are under construction to house elevators, escalators, and entry plazas. And their architecture is designed to blend into the East Harlem streetscape while providing robust access and emergency egress. Trackbed installation, power systems, and signal infrastructure are proceeding simultaneously within the finished tunnel sections. The project uses modern communications-based train control technology, allowing for greater train frequency and precision across the extended Q line. The overhead power distribution is replaced by traditional third rail, integrated with new traction substations and protected emergency walkways lining the entire tunnel route. The new 125th Street Terminal Station presents unique engineering conditions as it interfaces with existing subway lines and Metro North at Harlem, 125th Street. Crews are constructing complex intermodal transfer facilities that will allow riders to move seamlessly between regional rail and the subway system, all while reinforcing the structural envelope beneath a heavily trafficked urban corridor. In the final months of 2025, construction crews are working on systems integration, fire suppression installation, ventilation ducting, tiling, lighting, and full-scale commissioning of all mechanical and electrical systems. Once completed, the new segment will connect tens of thousands of East Harlem residents to the broader subway network, shortening commutes and easing congestion along the overburdened Lexington Avenue line. When Phase 2 of the 2nd Avenue subway opens at the end of 2025, it will mark another critical chapter in the gradual fulfillment of a transit line first envisioned in the 1920s. It delivers not only enhanced service to the Upper East Side and Harlem, but also long overdue transit equity to a neighborhood that has waited generations for high-capacity subway access.
Candlestick Point and Hunters Point Shipyard are among the most active megaprojects in San Francisco as of 2026. Spanning more than 700 acres along the city's southeastern shoreline, this redevelopment effort is in full swing. reshaping two long-neglected sites into a new urban district. Construction is progressing across multiple parcels, with new streets, housing blocks, and parks taking shape, setting the stage for what will become one of the largest residential and commercial expansions in San Francisco's modern history. At Candlestick Point, where the old stadium was demolished years ago, heavy machinery is grading land for the first wave of residential and retail construction. Multiple mid-rise buildings are rising along a newly gridded street layout. These early phases, expected to complete between 2027 and 2029, will include thousands of homes, many designated as affordable, as well as the backbone of a future retail corridor and public transit connections. Parks and green infrastructure are being built alongside housing, integrating sea level rise protections and climate-resilient landscaping directly into the urban form. To the north, at Hunters Point Shipyard, development is further along. Phase 1 construction is already well underway, with completed townhomes and condos beginning to fill with residents. Additional parcels are actively under construction in 2026, adding new units monthly. Commercial spaces, artist studios, and civic buildings are also under development. Part of the project's goal to restore not just housing, but economic vitality to a part of the city long cut off from opportunity. When fully built out in the early 2030s, the combined Candlestick Hunters Point project will deliver over 12,000 new homes, more than 300 acres of open space, and millions of square feet of office, retail, and cultural uses. It's a complete neighborhood emerging from land that was, for decades, contaminated, fenced off, and largely abandoned. What's distinctive about this project in 2026 is its physical and social scale. This isn't a small infill development or a single commercial tower. It's a city-scale expansion happening within the city limits. Infrastructure is being laid from scratch. Power grids, sewer lines, transit loops, and broadband networks are all part of the foundational work occurring now. Major sections of waterfront are being rebuilt with ecological restoration in mind, with plans for habitat zones, walking trails, and public piers that will eventually reconnect residents with the shoreline. Affordable housing is a central element of the development, and 2026 marks a critical point as the first large wave of affordable units nears completion. These are being reserved in part for legacy residents of Bayview Hunters Point, addressing historic displacement and economic exclusion. Community input remains part of the planning process, particularly in shaping local hiring programs and cultural preservation efforts. Construction challenges remain. Environmental safety is closely monitored due to the site's naval and industrial history. Some parcels require more remediation than others, which is influencing the pace of development. But in terms of raw activity, cranes, crews, and square footage under construction, Candlestick Point and Hunters Point Shipyard rank among the most dynamic megaprojects in San Francisco right now.
A massive rail yard into a walkable, mixed-use urban district is a construction undertaking that combines demolition, structural engineering, and urban infrastructure on a scale rarely seen within the core of a major American city. Centennial Yards in downtown Atlanta is a prime example, involving the redevelopment of former gulch land, an underutilized expanse of sunken rail corridors and viaducts, into a vibrant network of buildings, roads, and public spaces layered both vertically and horizontally. The site's existing condition presented immediate challenges. Large portions of the project footprint sit below street grade, surrounded by elevated roadways and crisscrossed by active rail lines. To establish a new ground level suitable for pedestrian circulation and vehicle access, construction crews first had to implement structural deck systems over sections of the gulch. These concrete and steel platforms supported on new pile foundations, create an artificial surface that connects to existing streets via ramps and vertical cores, while spanning over active rail infrastructure below. Before those platforms could be built, crews performed selective demolition of obsolete concrete retaining walls, drainage structures, and derelict freight infrastructure. Simultaneously, extensive underpinning and structural reinforcement were carried out on adjacent viaducts to preserve structural integrity during nearby excavation and pile driving. Soil nailing and shotcrete were used on vertical cut faces to maintain stability, especially in narrow work zones, where deep excavation was required next to functioning roadways. As the platform structures took shape, the installation of new utilities proceeded in parallel. Stormwater drainage systems were installed beneath the platform decks using precast concrete pipes and box culverts, routed toward detention vaults and outfalls, capable of handling peak flow from large roof areas and paved surfaces. Domestic water, fire protection lines, electrical duct banks, and fiber conduits were all routed through newly constructed utility corridors, integrated with service cores that penetrate the platform deck and provide vertical circulation and access. With the new artificial grade in place, above-grade vertical construction could proceed. Foundations for the buildings included deep, drilled piers extending through the deck system into stable substrata. Structural steel framing, composite concrete decks, and curtain wall systems were erected using tower cranes mounted on temporary footings above the platform. Mechanical systems, such as air handling units, cooling towers, and electrical switchgear were installed in shared utility basements located between buildings, designed for centralized operation and future capacity expansion. The layout of Centennial Yards required tight geometric coordination between new construction and existing urban elements. Street alignments, bridge connections, and pedestrian access points had to match the city's existing grid while introducing new mobility elements like bike lanes, wide sidewalks, and mass transit access. Specialized paving systems were used on pedestrian corridors, including permeable pavers and decorative concrete tied into tree wells and biofiltration zones for stormwater treatment. Before the first runway grading begins, the Southern Nevada Supplemental Airport is being conceived as a large-scale airfield designed to relieve pressure on the heavily used Harry Reid International Airport. The location, set in the Ivanpah Valley south of Las Vegas, drives much of the engineering approach. Planners must contend with desert soil conditions, high summer temperatures, and seasonal winds, all of which affect runway orientation, pavement design, and operational layouts. Initial site preparation would start with extensive grading to create level surfaces for runways, taxiways, and terminal areas. Given the scale of a major airport, this would involve moving millions of cubic yards of material, compacting subgrades, and stabilizing any loose sands to prevent future settlement. Dust control measures would be constant, with water trucks and soil binders deployed to meet environmental requirements and protect nearby communities from airborne particulates. Runway construction would follow FAA specifications for length, width, and load-bearing strength, accommodating large commercial aircraft such as wide-body jets. Pavement design would likely involve a layered structure of stabilized subbase, aggregate base, and high-strength Portland cement concrete capable of withstanding the concentrated loads from landing gear. Each slab would be doweled and jointed for load transfer and thermal expansion, with embedded lighting fixtures for night and low visibility operations. Taxiways and apron areas would be built to the same high standards, but with added flexibility for ground handling equipment, fueling operations, and aircraft maneuvering. Underground utilities, electrical conduits, fuel hydrant systems, water supply, and storm drainage would be installed in parallel with pavement work to avoid costly future excavation. The terminal complex would require deep foundations to support multi-story structures, as well as integration of baggage handling systems, passenger boarding bridges, and high-capacity HVAC systems to maintain comfort in extreme heat. Structural steel framing would provide large, column-free interior spaces, while exterior glazing systems would be engineered with solar shading to reduce heat gain. Air traffic control facilities would include a control tower with unobstructed sightlines over all airfield operations, supported by radar, communications equipment, and backup power systems for uninterrupted service. Support buildings such as maintenance hangars, fire and rescue stations, and cargo handling facilities would be strategically placed for rapid response and operational efficiency. Once operational, the Southern Nevada Supplemental Airport would be a fully integrated transportation hub, engineered from the ground up to handle high passenger volumes, large aircraft, and the demanding conditions of the Mojave Desert, while ensuring capacity for the region's growing air travel demands well into the future. Instead of beginning with tracks or vehicles, the Green Line LRT in Calgary was initiated through a comprehensive utility relocation and ground improvement program. Before any vertical construction or tunneling could proceed, dozens of kilometers of buried infrastructure, stormwater pipes, sanitary lines, electrical ducts, and fiber optics had to be identified, protected, rerouted, or upgraded. In several locations, these utilities intersected at dense nodes beneath arterial roads and future station sites, requiring meticulous planning and trenchless methods such as micro-tunneling and pipe jacking to avoid service disruptions in heavily trafficked areas. Once the utility clearance phase was sufficiently advanced, work progressed into the early stages of civil construction. The Green Line, spanning a mix of underground, elevated, and surface-level segments, called for an array of structural systems. In the downtown core and Beltline areas, tunnel construction formed a significant portion of the work. This involved sequential excavation methods with the use of temporary steel ribs, shotcrete, and soil anchors to support the advancing tunnel crown in low overburden areas. Where ground conditions allowed, pressurized face tunnel boring machines were scheduled to be deployed, operating in glacial tills and mixed soils with varying water tables. Tunnel station boxes, such as those planned beneath 2 Street SW and Center Street, demanded deep excavations in urban zones flanked by high-rise foundations. For these station caverns, diaphragm walls or secant piles were used to form rigid shoring systems, and ground freezing techniques were planned for groundwater control and soil stabilization in permeable layers. Real-time instrumentation was installed throughout excavation zones to monitor settlement, vibration, and deformation, with automated feedback loops to adjust construction parameters as needed. Outside the core, where the line transitions to surface and elevated alignments, earthworks and structural pier foundations dominated. Embankments were constructed using engineered fill, layered and compacted to specific densities, while concrete piers for elevated guideways were drilled into bedrock or dense till strata. Precast guideway segments were manufactured off-site and transported to staging areas, then lifted into place using mobile cranes and segment lifters, particularly for long spans over roadways and rail corridors. The vehicle maintenance and storage facility, a critical component located in the Shepard area, was built early in the project timeline to serve both staging and future operations. It included track work for vehicle testing, inspection pits, overhead catenary systems, control centers, and heavy-duty paving designed to handle the specialized weight and turning radii of light rail vehicles. Concurrently, track installation began using both embedded slab track in urban areas and ballasted track in outlying zones, with special attention paid to noise and vibration attenuation through resilient rail pads and floating slab systems. The Green Line stations varied significantly in typology, from fully underground platforms to elevated and at-grade stops, with canopies and weather-protected waiting areas. All station designs incorporated accessibility features, tactile warning strips, and provisions for future system expansion. Pedestrian connections, public realm integration, and intermodal transfers were key design drivers, particularly where the line intersected with bus corridors or major arterial roads. At the heart of a massive cross-border logistics corridor between Detroit, Michigan, and Windsor, Ontario, the Gordie Howe International Bridge emerges as one of the most technically ambitious and strategically vital infrastructure projects in North America. Designed as a cable-stayed bridge with an unprecedented main span length for this type of crossing in North America, the structure addresses not only current transportation needs, but also anticipates decades of future commercial and passenger vehicle growth. What sets this project apart is the integration of border processing facilities on both ends, a multi-use path for non-motorized users, and a focus on minimizing environmental impact during construction. Construction of the bridge began with an intensive ground improvement phase. On both the Canadian and American sides, the project required deep foundation stabilization due to soft soils and industrial legacy conditions. Thousands of concrete-filled steel piles were driven deep into the ground, many over 150 feet long, to support the massive load of the main pylons and approach structures. Vibrocompaction and dynamic replacement techniques were also applied in select areas to densify weak soils and ensure long-term settlement control. The signature feature of the bridge is its cable-stayed main span, which stretches more than 2,500 feet across the Detroit River. The two massive towers, each rising nearly 150 meters above the water, were constructed using climbing formwork systems with high-strength reinforced concrete placed in lifts and allowed to cure under strictly controlled environmental conditions. Each lift required careful coordination of embedded rebar cages, conduit for internal inspection systems, and multiple layers of quality control for alignment and geometric accuracy. The stay cables are arranged in a semi-fan pattern and connect to a composite steel concrete deck that is fabricated in modular segments. These segments are lifted into position by strand-jacking gantries placed atop the towers, and then post-tensioned into place as the structure progresses outward from both pylons in a balanced cantilever method. Because of the immense forces involved, cable anchorage zones in the deck were heavily reinforced and constructed using high-performance concrete to prevent cracking and fatigue over the bridge's lifespan. In parallel with the main span construction, the approach structures required extensive use of precast girders and segmental concrete box girders, supported on piers founded on deep drilled shafts and pile caps. Each approach segment had to be aligned precisely with the main span geometry to allow seamless connection once the cantilevers met at mid-span. Expansion joints, seismic isolation bearings, and cable dampers were installed to accommodate temperature changes, traffic vibrations, and potential wind-induced oscillations. Perhaps one of the most unique aspects of the Gordie Howe International Bridge is the inclusion of full customs and inspection plazas on both sides of the river, which had to be constructed concurrently with the bridge. These facilities involve complex building systems, large-scale pavement infrastructure, and real-time data integration with transportation networks. Stormwater management, energy efficiency, and border security technologies were embedded into their design from the outset. Stretching westward beneath one of the most densely developed urban corridors in Southern California, the Los Angeles Metro D-Line extension is entering the final stages of construction as of October 2025. With a phased opening scheduled for completion by the end of this year, this megaproject represents a critical leap forward in expanding LA's heavy rail subway system through some of its busiest residential and commercial neighborhoods. The full extension covers approximately 9 miles of new twin-bore tunnel running from the current terminus at Wilshire Weston all the way to the Westwood VA hospital area. The alignment passes through key transit and employment centers such as Miracle Mile, Beverly Hills, and Century City. Each segment is being delivered in phases, with multiple tunnel boring machines operating in parallel to meet aggressive construction milestones. These TBMs are designed to navigate a range of subsurface conditions, including tar sands, methane zones, and seismically active faults. They are equipped with pressurized slurry systems to manage ground stability while maintaining advanced rates through varied geology. As the twin tunnels are completed, crews install precast concrete lining segments, waterproofing membranes, and internal drainage channels, creating a continuous sealed tunnel environment rated for seismic durability and long-term structural integrity. Once structural works are complete, systems contractors follow closely behind with track installation, traction power infrastructure, and signal systems that connect seamlessly with the existing D-line operations. The new stations are constructed as deep excavations using a mix of cut and cover and mined cavern techniques, depending on the local urban constraints. At key locations like Wilshire, La Brea, and Wilshire Rodeo, station boxes are built with multi-level platforms, mezzanines, and pedestrian connections that interface with existing street grids. Each station includes full ADA accessibility, platform screen doors, modern lighting, and energy-efficient mechanical systems. Special vibration isolation measures are incorporated to protect nearby buildings and cultural institutions, including museums and historic properties. In 2025, the primary focus is on station fit-out, systems integration, and final testing. Crews are completing tiling, lighting, faregate installation, escalators, elevators, and back-of-house control rooms. Simultaneously, dynamic train testing is underway along finished segments, with test trains operating under full load conditions to validate propulsion, braking, ventilation, fire safety, and signaling systems. Communication-based train control systems are being commissioned to allow for higher frequency automated operations that match the rest of the Metro Rail network. At the project's westernmost end, near Westwood, special engineering attention has been given to interface with the nearby Veterans Affairs campus and prepare for future linkages to the forthcoming Sepulveda transit corridor. Portal structures, emergency egress shafts, and ancillary facilities are nearing completion, alongside power substations and communications hubs.
In 2026, one of San Francisco's most strategically important megaprojects under construction is taking shape across the Caltrain rail yards in the heart of central Soma. This isn't just a housing or transit upgrade. It's a massive reimagining of over 20 acres of publicly owned rail-adjacent land that has long divided the neighborhood. As construction pushes ahead this year, the rail yard redevelopment is steadily moving from planning to reality, with early phases under active build-out and long-term infrastructure elements aligning with the city's broader transit goals. Right now, in 2026, the site is in the thick of foundational construction. Crews are laying the groundwork, literally, for what will eventually be a dense, mixed-use district layered above and around the working Caltrain tracks. This megaproject is part of a coordinated effort to modernize regional transportation while unlocking thousands of new homes and millions of square feet of development potential just blocks from downtown San Francisco. The Caltrain yard has been a physical and visual barrier in central Soma for generations. But in 2026, construction is actively transforming this space into an urban connector. Elevated platforms, decked structures, and street-level improvements are all in progress, designed to bridge the gap between surrounding neighborhoods and the core rail infrastructure. This year, much of the work focuses on realigning utilities, stabilizing the site for future vertical construction, and preparing parcels that will be used for new housing, office towers, and public spaces. The housing element of the rail yard redevelopment is one of the most anticipated components currently under construction. Phase 1 will deliver several hundred new residential units, with a significant portion allocated for affordable housing. These buildings, now rising on the edges of the yard, are expected to be ready for occupancy by 2028. Eventually, the full build-out will add thousands of homes to one of the city's most transit-rich locations, housing that is critically needed as San Francisco continues to face supply pressures. But housing is only one piece of this megaproject. In 2026, work is also underway on commercial development that will bring job space to the corridor, particularly targeting sectors like life sciences, tech, and creative industries. The close proximity to both downtown and future rail connections makes this site highly desirable, and the ongoing construction reflects the urgency to activate it. Several mid-rise office buildings are being framed out this year, with completion of the first wave of commercial space projected around 2029. A crucial component that's being integrated into the redevelopment in real time is transportation. The Caltrain facility itself is being reconfigured to prepare for electrification, high-speed rail integration, and potential undergrounding as part of the downtown rail extension. In 2026, while major tunneling has not yet reached the yard, planning and structural coordination are fully underway to make sure future rail service, including high-speed trains, can be accommodated. This makes the rail yard site not just a place to live and work, but a critical node in the future of statewide transit.
Any given day, the Hampton Roads Bridge Tunnel serves as a critical artery for transportation in southeastern Virginia, and expanding this corridor demanded an engineering response of significant scale and complexity. Initiated to alleviate chronic congestion and prepare for growing regional demand, the expansion focused not only on capacity improvement, but also on increasing structural resilience, environmental sensitivity, and long-term operational reliability. The keystone of the project involved the construction of a new twin-tube bored tunnel under the Thimble Shoal Channel, an endeavour that introduced tunnel boring technology to a region traditionally reliant on immersed tube methods. Site preparation began with extensive marine surveying, geotechnical borings, and environmental studies to ensure that dredging, pile driving, and excavation would proceed without destabilizing the existing infrastructure or causing adverse ecological impacts. This was followed by the mobilization of massive temporary trestles and staging areas built along the edges of the Hampton Roads waterway, where precast elements, equipment, and construction materials could be stored and deployed efficiently. Floating equipment such as crane barges, tugboats, and supply vessels formed a coordinated logistics network, essential for moving large-scale items such as precast tunnel lining segments and rebar cages to the offshore tunnel portals. The new tunnels, constructed using a tunnel boring machine specifically designed for the unique soil and hydrostatic conditions of the region, began with the launch pit on one side of the channel. The TBM was assembled on site in a specially excavated pit lined with slurry walls and reinforced with steel bracing. As the TBM advanced, it excavated through layers of clay, silt, and sand, simultaneously installing precast concrete segmental linings to form the circular tunnel structure. Each segment was set in place using hydraulic arms with gaskets to ensure a watertight seal, and the annular space behind the lining was grouted to prevent settlement or water ingress. Parallel to the tunnel construction, bridge widening and interchange improvements on the approach roads were carried out. This required staged demolition and reconstruction of existing structures, new pile-supported bridge spans, and lane realignments. Precast, pre-stressed concrete girders were lifted into place using heavy lift cranes, and cast-in-place decks were poured using travelling formwork systems. The sequencing of this work had to be tightly coordinated with ongoing tunnel operations to avoid disruption to traffic and construction activities. Ventilation buildings, fire suppression systems, and emergency egress pathways were integrated into the tunnel design to meet stringent safety requirements. The mechanical and electrical fit-out included high-capacity jet fans, LED lighting arrays, and a suite of sensors and control systems connected to a centralized monitoring facility. Waterproofing, corrosion protection, and redundancy in utility lines were also built into the system to account for the harsh marine environment. Launched from the earliest stages of planning, the construction of the Venetian in Las Vegas was envisioned as both a large-scale hotel and a themed architectural reproduction of Venice's iconic landmarks, requiring careful integration of structural engineering with elaborate facade detailing. The project began with deep foundation work, as the sheer height and footprint of the resort demanded a robust support system. Pile foundations and reinforced concrete mat slabs were installed to distribute loads evenly across the variable desert subsoil, with strict tolerances to accommodate the superstructure's alignment. The main tower and podium levels were built using a reinforced concrete frame for strength and fire resistance, while structural steel was introduced in key areas to allow for larger spans and open interior spaces, particularly in the casino floor and grand lobby. This combination of materials provided both rigidity and flexibility in meeting design requirements. The building envelope had to be engineered to withstand the extreme heat of the Mojave Desert while supporting ornate architectural elements, stone cladding, decorative moldings, and replicas of Venetian arches and columns, without compromising structural integrity. Mechanical, electrical, and plumbing systems were integrated early in the superstructure phase to serve the massive volume of rooms, retail areas, restaurants, and entertainment venues. High-capacity HVAC systems were distributed through mechanical floors, with ductwork routed in concealed chasers to maintain the interior's thematic authenticity. Plumbing networks were particularly complex, supporting not only the thousands of guest rooms, but also the extensive canal and fountain systems that define the property's public spaces. The Grand Canal itself required specialized water engineering. A reinforced concrete basin lined with waterproof membranes was constructed to hold the waterway, while concealed pumping and filtration systems kept the water clear and flowing. Load calculations for pedestrian bridges and canal-adjacent structures ensured both safety and the realistic aesthetic of Venetian streetscapes. Interior fit-out work was equally intricate. Large expanses of stone flooring, decorative plaster ceilings, and imported materials were installed with a combination of modern fastening methods and old-world craftsmanship techniques. Lighting systems were carefully tuned to highlight architectural details and simulate the soft ambiance of Venice, while still meeting safety illumination standards for a high-occupancy building. As the final stages progressed, the integration of themed architectural features with state-of-the-art hospitality infrastructure made the Venetian a unique challenge from an engineering standpoint. When completed, it stood not only as a luxury destination, but also as a highly complex, large-scale building system disguised beneath a meticulously crafted facade that captures the essence of its namesake city.